सर हे कोर्सचं मटेरियल चांगलं आहे सर नंतर वापरायसाठी.
म्हणजे जे टाकलेलं आहे ते Moodleवर?
हो सर, Moodleवर आणि हे ऑनलाईन लेक्चर्स आत्ताचे.
आपण चांगलं केलं ना युट्यूब चॅनल.
हो सर, ते ऍक्च्युली लॉंग टर्म सुरू झाला सर तो.
लॉंग टर्म सोर्स झाला. एक्झॅक्टली. आता फक्त युट्यूबने त्याला कधीतरी हे करू त्रास देऊ.
हो सर. नाही तर सर म्हणजे 6 महिन्यानंतर ते
बरोबर
पाहावं पण
आहे.
लागतं जेव्हा लॅब घेतो तेव्हा परत करावं
बरोबर आहे. आणि हे काय Moodle तर आपल्याला करून टाकावं लागेल ऍक्सेस नंतर, कारण Moodle साठी डिसेबल करावं लागेल. मी डाउनलोड करून पण चॅनल युट्यूब ते तर मस्त झालं ना परमनंट.
हो सर, परमनंट झालं ते.
आणि रॉकीचे सेशन वगैरे एकदम छान आहेत ते बघायला. गुड मॉर्निंग हसन सर.
Good morning, Surya sir.
गुड मॉर्निंग.
How are you today?
या फाइन. आप कैसे हैं सर?
मैं ठीक हूँ बिल्कुल. I'm absolutely fine.
वेरी नाइस. तो 5 मिनट रुकते हैं, 5 मिनट बाद फिर शुरू कर देंगे.
5 मिनट बाद. हाँ ठीक है, तो मैं
हाँ.
okay, I'll relax a bit. Okay.
ओके क्योंकि तब तक लोग ज्वाइन हो जाएंगे. Sneha madam. Next slide. Manisha madam, shall we start?
Yes, sir. Good morning, everyone. Myself, Professor Manisha Bansode, welcomes you all to AICT sponsored STTP on VLSI design using cadence tools, mixed signal design. It is a great pleasure for me to introduce our speaker for today's morning session, Dr. Mohammad Hassan, sir. Professor Hassan has been working as a full professor since March 2005. He serves as a chairman of department from 12th October 2015 to 11th October 2018. He completed his PhD from the University of Edinburgh, UK, on a Commonwealth scholarship in the area of low power architectures for signal processing and communications. He also worked as a visiting researcher on his own Royal Academy of Engineering, UK, funded project on low power FPGA in the same university. He has published 161 papers in the refereed journals and the conferences with 1,401 citations, H index 20 and I-10 index 44. This also includes 15 IEEE transactions or journals and 47 Scopus Index journals publication. He received Paper of the Year award by the editors of the famous international ETRI journal for his paper entitled High Performance Low Power FET course along with a Best International Conference Paper award. He has supervised 8 PhDs and currently supervising 4 more along with many MTech dissertations. He also delivered several keynote addresses and invited talks in conferences and workshops. He has filed 3 patents on the design of magnetic RAM, MRM, and 1 patent on robust SRAM. His research interests are in VLSI design, nanoelectronics, ultra-low power design, spintronics, batteryless electronics, variability-aware design. He is also a senior member of IEEE. Welcome, sir. I request to join the today's session.
Thank you. Thank you very much for the introduction. Shall I have to start the proceedings straight away?
Pleasure, sir.
And thank you
Yes,
for
sir.
giving me an opportunity to introduce this very important area in the current scenario. What I'll do is I'll start straight away by sharing my slides. Are my slides visible and am I audible?
Yes, sir. Audio, video, both clear.
All right. Okay. So let me start because I think this is a very generic audience. So I'll devote a lot of time on the basic stuff so that everybody really understands and appreciate the area of low power without going into specific architectures, because that will be too much for a general audience. So a major part of it will be devoted to low power techniques in general, which can be applied to any architecture, and then some specific techniques with respect to a signal processing, especially. So that's what I intend to cover today, so that the audience will have an overall feel of the low power area in general, and then of course specific to these particular areas. So let's start with the with today's agenda. I am Professor Mohammad Hassan, and of course, as is now clear with the introduction, and I've been serving the Legal Muslim University for the past, I think, around 28 years. The outline, I'll start with because I assume a generic audience, so some background stuff and motivation. A very few slides on the MOS transistor, because that will help in understanding the area of low power design. And then we have to identify what are the sources of power dissipation in CMOS. And then in general, how we can really, once we have understood the different types of sources of power dissipation in CMOS, then what are the different power reduction techniques which can be applied at, let's say, design time. Whenever you are designing some new product or some new architecture, some new algorithm you are coding for a given architecture, then at design time, what you could do. Now, if the system is in standby, when it's not active, when your mobile phone is not being used, still it consumes some power. And so we have some techniques, low power techniques, which can be applied in what's called the in the standby mode. So we must have techniques which can be applied in the standby mode. So we'll talk about the different techniques which are available in this standby and how we can really combat the standby power consumption, which is really one of the biggest challenge today, how to combat the standby power consumption. And then, of course, during runtime, depending on the load, at times the processor is engaged, at some other times it's a bit idle. So I think it's a variable load. So how we can effectively apply low power techniques at runtime under variable load scenario. So there are three different really subdomains of the power reduction techniques. What are the techniques which you can apply at design time, then at the standby mode, and then the runtime? And then there's a very important area which is upcoming, especially what's called the batteryless electronics. And you must be aware of, it's a big buzzword today, the word of IoT, where you have a huge number of nodes available at remote locations primarily for sensing. And maybe some actuation is also a part of it. Primarily sensing is a major part. And these nodes, they are doing some very basic functions in general, most of the nodes. So the power consumption of these nodes should be such that I really don't want to go into the remote areas and change the batteries all the time. So these nodes should be self-powered, or they should not have batteries. Maybe they can just derive power through maybe solar, through wireless means, or maybe through some vibration. So they have to really scavenge for power from the environment. And so these nodes should consume a power lower than a microwatt. So how we can design nodes, of course, it's a really big challenge, which can really consume a power lower than 1 microwatt, or maybe even further down, and still do the job, because these nodes are operating at a very low throughput, maybe in the kilohertz range or a low megahertz range, at which we can really think about trying to reduce the overall power below what's called below a microwatt range, if that is our reality, so that we really enter into the era of what's called the batteryless electronics, where we don't really have to charge the battery, change the batteries all the time. And then, of course, I'll talk about some specific low power architectures from the DSP world, because that's also very, very important, how the basic techniques we can really apply onto an architectures, and how we can really make them low power. And then, of course, what are the future possibilities in this area? So let's start going with some background stuff and motivation, so that you can really have a feel of this area to start with. So let's move ahead. So let's start with what's called the evolution of electronics. So starting from the 1850s to the 2025. So if you look at this, these transitions, starting from mechanical to electromechanical, vacuum tubes, the bipolar, the NMOS, and the CMOS. One thing which really contributed towards this transition is the power consumption. So this is some of the real reason behind the switch over from NMOS to CMOS. People used to say no static power consumption in CMOS because the load transistor and the driver transistors will never be on at the same time under static conditions. When the inputs are not changing, you have there's no possibility of any current flow between supply and ground. So when things are idle, this doesn't consume power. Of course, the reverse is true today. It does consume power, but when CMOS came, it was a big improvement over NMOS. And that was the primary reason why CMOS really became popular, of course, despite so many other reasons. But this is one of the very important reasons for the popularity of CMOS. So in general, it was all performance-driven, cross-driven, of course. And the scalability, you all know, is we are able to reduce the transistor dimensions so as to improve the performance as well as to reduce the cost. And that has been the story for the past 40, 50 years as far as the microelectronic industry is concerned. So let's move ahead and try to further refine this slide with the help of what is the real advantage of these all transitions. So look at this, the first one. The first one is the area, of course, the form factor. As we move down, of course, the transistor size is going down and down. And today the technology is, of course, 5 nanometers, and shortly we are moving to the 3 nanometer node. So you can yourself gauge it's sub 10 nanometers between source and drain. Transistor is remarkably small. Then, of course, if the transistor is small, lower capacitances, lower distances to travel between source and drain. So the delay goes down. So the delay, you're getting improved performance, more throughput. And then, of course, the capacitance goes down per transistor. The energy per transistor also goes down. That's another driver for scaling. And above all, the industry is surviving. The cost is going down, even today, the cost per transistor. So as long as the cost per transistor is going down, the scaling will continue. Unless, of course, things are becoming difficult, but still the cost per transistor is going down. As long as this continues, the scaling will continue in the future. But of course, there are huge challenges today. And I'll tell you in future slides what is one way of overcoming these challenges, which is something which has come up very shortly, and that offers a real hope of increasing the level of integration without further miniaturizing the transistor dimensions, which is becoming too much challenging today. Okay, so this is the slide which I'm really interested in. So transistor count, the chip size is, let's say, one inch by 1 inch, around 2 centimeter by 2 centimeter, and then within that, it's an slightly old slide from Intel. The transistor is 1 billion. But if I talk today, I'll take an example of an NVIDIA GPU, the latest one, which is around 54 billion transistors. And repeat, it's 54 billion transistors on a 1 inch by 1 inch chip size. Look at the transistor count, 54 billion transistors. And if you put so many transistors in such a small area, you can yourself gauge, although the transistor power goes down, but the power density, the power consumed per unit area is huge, And that's a real challenge. How to cut down the power density, as will be clear in the next slide. But the real problem, why the power has become so important, is the transistor per unit area is the density of the transistor is really high. 54 billion transistor in a 1 inch by 1 inch is a real challenge. But one thing which is just some additional important thing which might be of interest to you is this is one company which has the name Cerebra has come up with a very interesting idea, which I think one or two companies tried in around 1970s, but they miserably failed. I have deliberately shown this on the left-hand side. You have a wafer. This is a silicon wafer, and then you cut the wafer into small chips. These small chips, one of them might be NVIDIA, this GPU, contains 54 billion transistors. So the new idea, the Cerebra, they have come up with a new idea. Why to partition? Why to just cut the wafer into chips? why not have what's called the wafer scale integration, where the whole wafer will behave as one chip. In 1974, I think I just forgot the name of the company, that company went bankrupt because they were not able to produce a working chip out of a wafer because of the defects. Because some of the chips will fail on a wafer because you cannot have a zero defect wafer. But, and because of those defects, the whole circuit malfunctioned in 1974. But Cerebras came up with this brilliant idea. Again, they have redo the same, they have tried to do the same thing, but they're quite successful. And why they're successful today? Because although there are defects, so if I have a full wafer, let's say the 8-inch wafer, I think, which has been worked upon by Cerebras, they have been able to fabricate a working chip on an 8-inch wafer. Look, it's a wafer, not a chip, cut a small chip, just a small part of the wafer. So they have basically the whole area of the chip is now the same as the area of the wafer, which is an 8-inch wafer. So now they're able to put 1.2 trillion transistor at a wafer level, and they've proved that that circuit is working. And you'll ask me a question: why? How does it work? So the whole idea is they've just they divided the chip into very intelligent portions, and some of the portions will malfunction because of the defect. But then they will remove those portions because they have redundancy of the chip. So the chip is really intelligent. So some of the portions might not be working, but they have done away with those things. And whatever others they are working, they are making use of it, and still they are able to make the whole system, whole wafer chip works. And they've demonstrated that idea. And if this idea is really successful commercially, they've done it once. They've done it. They've showed it as a proof of concept. But then if it is repeatably, then it's a very attractive thing because now the whole wafer is available for a chip. You can yourself gauge if a 14-inch wafer is available for chip making, then you can really make huge number of chips without further scaling the dimensions of the transistor. It's a very attractive area, but of course, it has to be still commercially proven on a bigger scale. They have proved it at a smaller scale, but then if they're able to scale up, it's a very interesting area in which the whole wafer is available for transistor and for chip making. So I think sky is the limit, especially in the area of AI, which is becoming very hard. You can really tap the resources which this wafer scale integration offers. So let's move to the main point again back. I was talking about the transfer count. So 54 billion transistors in 1 inch by 1 inch. The power density was a huge challenge. So let's start now with the actual topic. So now transfer count, huge. So that's the reason why the power is a big menace, power density. Frequency was very low earlier on. Now the frequency is rising, and you'll come to know very shortly that frequency is also one very important parameter, which is responsible for power consumption. Because when things switches zeros to ones and ones to zeros, only then you have to charge and discharge the load capacitance. And for that transitions, you need to draw current from the supply voltage. And you need energy for that transition. So the number of transition is more, 0 to 1 and 1. That's because it depends, those transitions depends on the frequency. Then of course, the power goes up. So the frequency is rising because you have more and more throughput requirement. And you must have noticed by now one very important thing, which I'll let you know in this set of slides while we're going through it, that earlier on in the 90s, Intel was just selling chips based on higher and higher frequency. Only one mantra. Okay, my chip is operating at that specific frequency. That's it, nothing more than that. But today, nobody really bothers about the chip frequency. Not very much, because most of the chips are operating at 3 gigahertz, 3.2 gigahertz. And as per the earlier prediction, today the frequency might have gone to more than 10, 15 gigahertz. But why it didn't happen? Because the industry, they realize that they cannot really make a 10 gigahertz chip. The reason being the power problem, because frequency and power are directly related. You cannot really control power density if the chip operates in 10 gigahertz. So they have found out a way out. Higher throughput, how you can get that required throughput without increasing the frequency. And that via media is what's called the multi-core or parallel processing. Why not employ multiple processor and achieve the required throughput? And all these processors they're going to operate at a lower frequency so that the power of the individual processor remains in control. And it has been proven that if you do this, you're still able to do the job from a power perspective in a much better way compared to if you increase the frequency of a single processor and try to extract a better and better throughput from a single processor. So we have really entered the multi-core era because of the power problem. So now, so the frequency was another challenge, that we have to increase the frequency, and power has a direct relationship with the frequency, as you'll be coming to know shortly. So let's move ahead. Now, because of this power problem, because of this frequency increment, look at this, and the number of transistor count increment, the power continues to rise. I think there's a dip in 1985 just because something, I think they moved to some other technology, or right. So look, I think this is again, I think 2000, but I think this curve is rising and rising. And today's the typical servers, the power is around 200, 300 watts, typical power consumed by the microprocessors and the GPUs, 300 watts. I'll just give you an example. It's very interesting. 300 watts, the power is consumed by a chip. If the supply voltage is 1 volt, 300 watts, look at the amount of current. 300 watts power, the chip voltage is 1 volt. Look at the current, 300 amperes. So it's mind-blowing current. A chip handling 300 amperes of current. It's like you have ampere level currents on chips. So the power lines must be able to handle those currents, otherwise the chip will burn out. So the design of power lines, there should be have a required cross section to really handle that amount of current, which really flows in high-end server chips, which are having, I think, 200 watts or maybe 300 watts of power. That's the typical rating of a high-end processors today, and that's a real challenge. How we can cool down those chips so that the power remains at 300 watts level. It must be a massive exercise, and then how to design the power line so that they can handle the required current at such a low voltage. So I can just give you a simple example. The supply voltage is 1 volt and the power is 300 watts. You have to find out the current levels. Some high ampere current. So let's move ahead. Now this is the biggest problem. Look, even in the 2000, the chip temperature, if you look at the motherboard, it's the same as the hot plate. You can really, people have used chips to cook egg. So that's a dual purpose. They've demonstrated that the chip temperature is really high. Even at high-end servers, it's around 70 degrees centigrade chip temperature. So the power density, as a thumb rule, should not go beyond 150 watts per centimeter square. Otherwise, it becomes too much to handle. That's the upper limit. So 150 watts per centimeter square. And the power density is a very huge challenge because you are putting more and more transistors in the same space. So the power density is going up and up and up. And this slide was really was a prediction from, I think, Shekhar Boker from Intel. And it was it's a very old slide. But this slide really it really grabs the chip power density challenge. So the most cited slides, I would say. And this shows that this showed that if nothing would have happened, the chip density would have reached that of a rocket nozzle. But then, of course, the researchers, there's a huge amount of research in the low power area, and we are still able to maintain the temperature to around this power density to less than 150 watts per centimeter square, even in high-end servers. And by doing that, the chip temperature will not go beyond 70 degrees centigrade. If we have various special cooling arrangement, maybe by by employing some very low temperature at times, like cryogenic cooling or something like that. So let's move ahead. So the chip power density really put an upper limit. This is the real driver of why you can't increase the frequency beyond a limit, why you can't operate everything at 5 volts, because you will come to know that the supply voltage has gone down just to control this chip power density, because at 5 volts TTL compatibility, you cannot really have a chip power density limited to 150 watts per centimeter square. So, and then you cannot have a frequency beyond 4 gigahertz, because then again, the power density, that upper limit, upper threshold, that barrier will be broken. And so these are some of the things why you cannot operate beyond let's say 1 volt or 1.2 volt supply voltage, all of a chip. So So then, of course, these are some of the techniques which I'm listing and which I'll be discussing throughout today's proceedings. What are the reasons behind this problem of power, which is now almost the same footage as performance and area. Let's move ahead. Another problem which is cropped up is because right now you have all the battery operated system, and then the battery technology is not really moving at a nice pace. It's not really evolving. It's almost saturation there. Not really much of an improvement in the technology. So we don't really have another option but to cut down the chip power. If you really want a reasonable battery life, I don't want to charge my mobile phone all the time because my battery technology is not really helping me out. And I want to put more and more functionality on the chip. And still I want a reasonable battery life. So the only way is I have to put more and more functionality. But then with that sort of functionality, I want to keep the power to the limits. And that's a huge challenge. And that's why we need a lot of innovations at the low power level, how we can, despite more and more functionality on the chip, how we can really control the power, its power within limits or energy, that's more important, so that the battery life, you can get a reasonable battery life despite saturation in the battery technology. Now, this is the biggest challenge, and I'll talk about it in detail later, but this is just like one more motivation. If my mobile phone is not really working, it's idle, still this mobile phone will consume power, and that power is your leakage power or the standby power. And you'll be surprised to know that the leakage power is almost at the same level as the dynamic power today in today's technology. So we must address these standby issues. When things are not working, when things are not changing, when my mobile phone is not doing any useful operation, still it consumes power. And that's not a small component. That's a major component, almost at par with the real dynamic power and is active. And it's one of the biggest nuisance, and it has to be curbed. Otherwise, my battery life will be impractical. So there are various techniques for doing this also, and that I'll be discussing later on. Let's move ahead. All right. So now, why the power matters? I'll just club all the things which I've really talked about into one, and maybe some add few extra points. So let's try to do the discussion here. The most important thing is the power density is so high. You want to keep the chip temperature within limits. So you need to have a chip and system cooling arrangement you have to do. You must have seen pins on the chip. You must have been special type of cooling in high-end servers which are coming in the market. I don't know, some liquid, some low temperature cooling arrangements they have to make. And so you have to really put a lot of cost goes into this. And then the system cost really rises if you're not able to control the power of the chip. So if you're not able to control the power of the chip, you have to pay extra in terms of this cooling cost. And that's not really a great idea from the economics point of view. Now, since I told you already the current level is so high, your power lines must be able to handle that sort of current level. So you must properly size the power lines, otherwise your reliability will be affected. So your peak power should be such that all the power lines will be able to handle that sort of peak current in your circuit. So you have to do sort of peak power analysis of your circuit and find out what's the maximum current that flows through your circuit, and your power line should be able to withstand that current. Only then otherwise the chip will fail. Then of course you all know this, the battery life for all we want really a very long. I don't want to charge the batteries all the time. And this is really I want ideally batteryless, but even if I have batteries, I just want to charge it less often. But still I have to do it almost after every other day. And then this means a lot of improvement, but it's a real challenge that we have to face. And then you have an era of what's called the IoT driven era of batteryless electronics, ultra low power design, where this is a very specialized area where I want to cut power and I don't bother about the performance because I need to sense and maybe I can operate in the kilohertz range. So power is the real motivation without bothering about the performance. So if that is the domain, then I can very aggressively reduce the power consumption to a level less than 1 microwatt, so that the reason behind it, I just would want to remove the batteries, maybe use supercapacitors, maybe use some other type of storage to charge my my IoT node without needing a separate power source, or maybe I have to do some sort of scavenging from maybe a wireless source, from maybe a solar, or some other sources of energy which are present in the environment, so that I can really it's just like a self-powered, self-contained system, and that will be very attractive from the IoT point of view. Then, of course, there are environmental concerns, as one office equipment accounted for around 3% of the total US commercial energy usage. And then one very interesting fact, which you may not be knowing, the cost of a data center is solely determined by the power bill. Look, I already told you the high-end servers, they are really consuming huge power. And these high-end servers, they are the server farms are there. If you have Google, if you have Facebook, if you have Twitter, if you have Instagram, all these social medias engines, and then of course they have massive storage data centers available. And you'll be surprised. I'll just show you one slide to make my point that these data centers, one thing is the cost of the data center is primarily determined by the power bill, because you must have especially air conditioning. And just to cut down the power bill, just like nuclear power plant, most of the data centers today, they are located in close to the river, so that we can use the water to really do intelligent cooling. And of course, one interesting idea which I came up is I think some of the companies, they are trying to explore the possibility of the location of these data centers that are basically seabed, so that the temperature can be controlled in a very effective manner without much of a nuisance. So this is really the power consuming data centers. So now it's not like only the battery driven. Even the high end server is a real big nuisance from the power perspective, and something must be done to cut down the power, despite all these sort of innovations which have been going on for the past 20-30 years. Let's move ahead. Now, really, before coming up with the sources of power consumption and this, so I'm about to finish one in 2-3 slides, the background stuff. So now I think the power is becoming so popular that now things are being defined rather than performance basis. They're also being defined on the power basis. And we talk about what's called the megawatt data centers, the microwatt wireless sensor nodes, and maybe the PDAs, or which is the laptops which are in the 0.1 to 1 watt range. So rather than MIPS, like the performance criteria, we want the systems to be defined in watts. And just because of the importance of the power area, maybe I can just, I think this is just a duplication of the same slides. We have the watt nodes, then the milliwatt nodes, and of course the microwatt nodes. The microwatt nodes are in this era of this, which is basically, this microwatt nodes are this in the area of what's called the IoT. Then you have the milliwatt nodes, primarily the mobile phones, the laptops, and all that things. Maybe they go up to watt or maybe more. And then you have the higher end servers, the watt nodes, and all these high Q video processing, where of course the main power is there. So you have just depending on the performance, high Q videos, or maybe sensing, you can categorize the different nodes in microwatts, milliwatts, and even the watt nodes. This is also one other way of looking at the same thing. Now, one very interesting slide to show, to have an analogy with nature. And this is a very thought-provoking slide. And I've deliberately inserted it to excite you so that a lot of things can be done in this domain. The way we have been doing it may not be the right thing. The human brain has got around 2% of the body weight. It does many important things, or most of the important things, and it consumes 20% of the total dissipation because it does a lot of important things. But the average brain power is just 20 watts. Look how efficient is the human brain. Despite all the complex thing it does, it only consumes around 20 watt of power. And I can, okay, I think I've just, that thing is not coming up. But one other source of information I have, if you really want to try to simulate even the rat brain on a high-end system, they've tried it. A rat brain simulation, if you do full simulation, it consumes around a megawatt of power. So what we have, von Neumann or maybe Harvard architecture, whatever architecture we have, they're so inefficient in terms of power. A human brain does the job. Or maybe, of course, I think we have tried with the spiking neuron. Even the spiking neuron is so inefficient that you need around a megawatt of power, even just to simulate in real time the mouse brain. So look at the gap in the efficiency of a human brain vis-a-vis the machines of today. So that the power density just 15 milliwatts per centimeter square, and today is it's 150 watts per centimeter cube, so, or maybe even more than that. So that's a real challenge. There's a huge gap, and maybe a lot of innovation is required so that if you can really mimic our circuits on the lines of the brain, if you really can create those circuits, then there's a big possibility of increasing the energy efficiency of those sort of circuits. Just to look at the brain, it's only 20 watts. And if you really want, even the mouse brain simulation in real time, and the power goes into the megawatt. So that's a thought-provoking slide at the efficiency difference between the human brain and what you get in actual machines. Let's move ahead. Now, before starting the actual topic of the sources of power dissipation and the review, so let's look at if I have a given problem, in how many ways I can to have the real feel of the area. If I have, let's say, a given algorithm, that algorithm can be from any area. Let's say I'll take, let's say, a very simple FFT algorithm, or maybe an FIR filtering algorithm, or maybe something from cryptography. Or now I can write for that algorithm if I really want to implement that algorithm. I can implement it in a very highly flexible environment, like on an embedded processor or on a general purpose processor. But the problem is a general purpose processor is not really designed keeping that particular algorithm in mind. It may not have the instructions designed for that algorithm. It's a generic machine. And therefore, this solution where we implement a given algorithm on an embedded processor or a general purpose processor, that's called energy inefficient. Look at this. This is highly energy inefficient. And the reason is because we have chosen an embedded microprocessor or a general purpose processor. And this embedded microprocessor or a general purpose processor is not really a good option because it has not been tailored to implement that absolutely algorithm. We can do it in a more energy efficient fashion by implementing the same algorithm on a domain-specific processor. Let's say if the algorithm is from the DSP domain, and we have really chosen, let's say, a DSP processor from Texas Instruments or from the ADSP, then of course things become more efficient because those processors are designed to implement the DSP algorithm, and therefore the energy efficiency rises. And of course, because we are using domain-specific processors, so the flexibility level might not be the same as that of a fully flexible embedded processor, or maybe so we can use a domain-specific processor to do the job rather than an embedded processor, when the energy efficiency goes up. So if we take the algorithm from different domains, we can design our own application-specific processors and try to do the job. Now, the third option is we can have what you call a configurable or paradigmable architecture. That is, now I'm not writing a code for these two options. I have to write the algorithm in a C code or on a MATLAB code and implement it. So these are what we call the software solutions for the same problem. But if I try what's called the hardware solution, so let's say I'll try the field programmable gate array option and try to implement that, or maybe some other reconfigurable architectures which are programmable, so that I can really make the changes if some new things comes up. So this is basically start from scratch. I can so as to make it the most energy efficient. In the first option, you have a generic instruction set, not really tailored for anything. On a DSP, it's better because the instruction set is tailored and the hardware also is tailored to implement the DSP algorithm so it becomes more energy efficient. But then on a reconfigurable stuff, you can design your own architecture, keeping the algorithm in mind. So you have big leverage. You can exploit that leverage to get the best possible energy efficiency. So energy, but then you have to pay, say, hardware stuff. So it has limited flexibility. So it's not like as simple as just changing the C code in the embedded microprocessor or maybe the domain specific processor word. Um, so my question, my thing is, it's less flexible, the hardware approach, but still you can do the changes because it's configurable. And if you still want better efficiency, configurable means you have to pay, you have to reserve some extra areas to make things reconfigurable so that you can make changes easily in the hardware. But if you want a purely hardwired or custom approach, a specific integrated circuit for a given you can choose any of the options available, and we can just give you an idea of how the energy efficiency and so a hardwired custom is more energy efficient. Reconfigurable systems where you put the algorithm, then of course the flexibility is there. If you do it on a DSP processor, it's faster and more energy efficient compared to a general purpose processor. So these are the implementation choices to start with for a given problem. And given problem can be an algorithm. So you can choose depending on what is your requirement. Is flexibility the most important thing for an embedded processor? Energy. Then you can design a hard your throughput requirement. The efficiency, but the big options, broad options, so that this is really a given problem, how you can solve it. So the flexible solutions are what's called the software to hardware solution, which gives you flexibility and throughput, but then at the cost of flexibility. So it's up to you which one you have to around the motivation. So and a generic view. Let's the sources of power dissipation in CMOS, and then I'll move ahead with the different types of reduction techniques. The agenda is it's like 10:45, so maybe I'll try to 45. We can break till 12, and then 1:15 I'll take up the low power. Points are related to the MOS trends. And I'll the important things which I really want to cover. Now, one thing which is most important depends on the difference between the supply voltage and the threshold voltage. We call this also an overdrive, VGS minus VT. So the difference of VDD and VT will decide the extent of the on current of the MOS transistor. Remember this very important thing, that the on current is proportional to, of course, for short channel, it will be just the VDD minus VT. I've just talked about long channel. And then look at this, it's also a strong function of mobility. That's the reason why, if I really want a large on current, we have to hunt for devices with higher and higher mobility compared to a traditional CMOS. Because then for the same overdrive, we will get a higher on current. And that's what we want, a higher on by off ratio, a higher value of on current and a very low value of off current. That's what the transistor should be. It should be a perfect switch. It should have a very large on current and a very small off current. So if you really want, now the trend is the supply voltage is going down. If the supply voltage is going down, if you want to maintain the on current, you also have to proportionally scale the threshold voltage. Because if you don't do that, this difference will go on reducing. So if you scale the supply voltage without scaling the threshold voltage, my VDD minus VT difference will go down, and therefore my on current will. If the on current goes down, so if my on current level goes down, more time will be required to charge. If the on current goes down, then the delay goes up. That is one very simple definition of how the on current relates with the delay. If I assume, of course, the fixed capacitance value. So remember this very important relationship, because this relationship will help you in understanding the low power techniques and what I will be going to discuss in the future, because this relationship is important. Remember, the on current is related to depends on the difference between the supply voltage and the threshold voltage. So the two most powerful knobs under the control of a low power designer is the supply voltage and the threshold voltage. Remember, I'm again reiterating, for the whole of this lecture, the two most important knobs under the control of the designer is the supply voltage of low power voltage and threshold voltage. These two voltages are the prime mover of the low power design area. This voltage to come up with different techniques for the low power design. So let's move ahead. Now, another thing is body effect. Now, threshold voltage, of course, it depends on the number of immobile charges present in the channel. So like we call the defletion. So if I start applying a voltage at the gate, first of all, there will be defletion. Now, so the threshold voltage depend on the amount of depletion charge. And this depletion charge can go up because you have this, this is a source, and below there is a bulk substrate. Now, this N plus P junction is reverse bias. So if I increase the reverse bias of the source and bulk, what will happen? The extent of these immobile charges will rise. Now, this extent of this immobile charges will rise, and therefore the threshold voltage will rise. So the threshold voltage depends on a fixed value which corresponds to when the source and bulk are at the same potential. That is, when there is no reverse bias between source and bulk. VT0 is the threshold voltage corresponding to the VSB equal to 0 when there is no reverse bias between the source and the bulk. And if there is a reverse bias between the source and the bulk VSB, then what happens is the reverse bias rises, the threshold voltage will also rise. This effect is body effect. Why? Because if the reverse bias goes up, the amount of depletion charge goes up, and these are negative charges. So if 10 negative charges goes up, on the channel. That is so that the channel is formed between drain and source. And therefore, if there are more immobile charges and more immobile charges, why I'm getting more immobile charges? It's because of the reverse bias goes up. And you know that if the reverse bias goes up, the depletion charge goes up in a reverse bias diode. So basically, it's increasing the depletion charge through the back door, source to bulk. And by doing that, I need more positive charges. If VSB goes up, the threshold voltage goes up. So this is a very important thing. That's why I'm discussing here. If the source to bulk voltage goes up, then the threshold voltage rises. And hence, as will be clear from the next slide, the the source to bulk voltage is a very important knob under the control of a designer because that will help in increasing or decreasing the threshold voltage. Remember this very important effect because I'll be making use of this effect in the low power design arena. That is, the source to bulk voltage is responsible for modulation of the threshold voltage because the two important knobs under my control as low power designer, they are the supply voltage and the threshold voltage, and the body biasing will help in controlling the threshold voltage, and therefore, as you'll be coming to know shortly, threshold voltage can be effectively controlled through body bias, and threshold voltage will play a very important role in controlling what's called the leakage power, as we'll be coming to know shortly. So this is something which you are supposed to know. Let's move ahead. And the last thing which I really want you to know in a simple MOS transistor is today the MOS transistor is never off. A nanoscale transistor is never off. It is fully on or it is partially on. That is, we assume that this is a plot of the drain current and the gate to source voltage of a MOS transistor. We assume that when the gate to source voltage is lower than the threshold voltage, or it's when VGS is less than VT, there is no drain current. That was not the case today. The current never becomes zero, just like it's not like this. As soon as the threshold voltage comes, the current will go down to zero. It's not like this function. That is, the current becomes zero straight away. The current will fall gradually. And how quickly the current will fall, that will depend on the subthreshold slope. So subthreshold slope, this is the area. How quickly the current will fall down, that will be a measure of the quality of a MOS transistor. If I can design a transistors where the slope is very sharp or very low, then it's a much better transistor. So today, if you really want to come up with a new transistor which is better than, let's say, a FinFET, then it should have a subthreshold slope of a much lower value than typically it's around 60. It's around 90 millivolts per decade is the subthreshold slope of an NMOS transistor. If you can design a transistor with, let's say, a 10 millivolts per decade slope, that's great. Why it's great? Because the problem is when the gate to source voltage is zero, look at this. This much of current is flowing. That's what the current is flowing through the MOS transistor. Why? Because the subthreshold slope is not very steep. It is 90 millivolts per decade. So even when VGS equal to zero, the current is not zero. And this current is flowing through. If I have 1 billion transistors, then all the 1 billion transistor will count. And just if you carry out the aggregate, then it's a massive value. That's a problem. Every transistor is partially conducting today. And then the biggest, one more big problem is in this region, we call it sub-threshold region, where the gate to source voltage is less than the threshold voltage. The relationship between drain current and gate to source voltage is exponential, just like a MOS transistor. So a small change in gate to source voltage will cause a very large change in the drain current. So the relationship is very sensitive between the drain current and the gate to source voltage in this very important area of what's called subthreshold. It is one of the biggest nuisance for the low power area. And the reason why, because the transistor is conducting even when it's not doing any useful thing. And every transistor is conducting. You can just go on adding, and you can then you can yourself gauge the amount of problem. Now I'll just give you a very interesting idea why this leakage power is such a big problem. Look at this. When the threshold voltage was 1 volt, I'll plot again the drain current. This is my drain current with respect to the gate to source voltage. I'll plot this very interesting. If I plot this, the gate source voltage is the so if I plot this ID and VGS, then what really happens is between ID and VGS, if the threshold voltage is 1 volt, then if I plot it, then it will be like this. So if the fall is like this, look at this. At 1 volt, there's no problem because even if it is 90 millivolts per decade, still when VGS equal to 0, the current is 0, no problem. But if you reduce the threshold voltage, let's say to 0.2 volts, then if I have the same slope, look at this, the current will be substantial. The voltage, the current will. So the problem is the drain current is exponentially, and that's a huge because of this current, which will come up at a very low threshold voltage. Talking about later on. So you must appreciate today on the extent of the subthreshold slope, and that's around fixed around 90 millivolts per decade for a power. So that understand. So that's the big problem with am I audible?
Sir, it is breaking. Your voice is breaking now.
Is it breaking? What can I do? Because I think it's nothing has changed.
Yeah. Now it is clear.
Okay,
Now
no, okay.
I'll
Okay, I have to hold it then. I have to hold the microphone. All right. So
now it is clear.
all right. Okay. So I'll have to hold it, right? All right. Now the width and length of a transistor today, because of the sub-wavelength lithography, there is actually in the length, especially if you have a variation in the length, you um, the source and drain um, distance is very, and the depletion layer will take care of a large portion of it. Therefore, the effective distance further goes down. So, if you reduce, basically rises. So that's a reduce barrier loading connection between the drain voltage and the if a drain voltage is higher, then the threshold voltage goes down. So these are the problems which we really encounter in a MOS trend. Only then you can appreciate the low power techniques which are employed to reduce the power consumption these domains. Now, okay, so I'll skip this slide. So let's move ahead and try to understand the sources of power consumption. Now, you all know this is what the average power consumption determines the battery life. Average power is the power consumed per clock cycle. That's how we define the average power. And of course, average power into time will decides the battery life. That's the energy. Now, peak power, as I already told you, the power and ground wiring depends on the peak power. If the peak power is more, then you have to really redesign the wiring so that the wiring can withstand the peak power. And then the packaging also will be able to handle the peak power. Otherwise, the system will burn out. Now, there are two major portions of power in CMOS, as you'll be coming to know shortly. One is the dynamic power, and the other is the static power. And the dynamic power depends on the activity. And you have a static power which doesn't depend on the activity. It's like without activity. When things are not really changing, then that's the static power. And of course, in these, the dynamic power component depends on the different operating modes, whether it's design time or standby or runtime, as shortly. Then, of course, the energy is the power into delay. Uh, uh, so that this slide will further explain the important thing between the power and energy. So look at this. There are two designs, two approaches for solving the same problem. In approach one, the power consumed is very large. Look at this. Compared to an approach two, where the power consumed is very small. But the time required in approach two is longer compared to the time required in approach one. So the thing is, if I compute the energy, power into time, both the approaches will consume the same energy. So the battery life depends on the energy. So just by looking at the power, you should not be confused with the battery life. It is the power into time that will decide the battery life. So energy is more important from the battery perspective than only the power. So you have to reduce, if I really want to compare two designs, then I must say that if the two design consume the same amount of time, then of course the power differential really is of any meaning. The energy is more important than power for the battery life, because from the first impression it seems that approach 2 is better than approach 1, because approach 2 consumes lower power than approach 1, but then approach 2 will take longer time to do the same job, and therefore the battery will be drained for a longer time. So the energy basically remains the same. The only thing is approach 2 is slower, that's why it's consuming low power. So from the energy, both the approaches is the same, although the power is different. So that has to be clear about it. If you the energy has to be compared if you want if comparison. All right. Identify components on that you really try to appreciate or discharge the load. To really charge and discharge the load capacitance. So the load capacitance either should be is where you want to extract the power from the one transition. You draw transition is ultimately the capacitance will be charged to VDD. So the zero transition is CV square. Will be lost somewhere. So components of can foremost required to discharge the capacitance. Energy now will be replaced by the supply voltage. VDDs, where CL is the load capacitance, VDD is the supply voltage. So, cycle, then the will decide probability is what, then the 0 to 1 trend.
Sir, your voice problem is breaking or not. Now there is no audio. Hasan sir. Hello. 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 Hasan sir. Has, Hasan sir.
Not audible?
No sir. In between, there was no audio for 3-4 minutes.
Okay.
सर वॉइस ब्रेक हो रहा है कंटिन्यूसली.
अब आ रहा है नहीं यार? अब आ रहा है?
नहीं यार सर, एक काम
Is it
कीजिए
coming
ना,
now? लॉग आउट करूं?
यस नाउ इट इज कमिंग. हाँ सर, लॉग आउट करके लॉग इन कीजिए एक बार, बहुत देर से इश्यू चल रहा है. मैं आपको नहीं करता हूँ वापस. नहीं सर, ब्रेक हो रहा है सर, कंटिन्यूस ब्रेक हो रहा है आवाज. सर आप लॉग आउट करके एक बार लॉग आउट करके लॉग इन
नहीं
कीजिए सर वापस. हाँ हेलो सर. सर लेकिन अभी आपका आवाज नहीं है. हसन सर, नो ऑडियो. सर ऑडियो नहीं है. आप म्यूट है शायद.
मेरे ख्याल में म्यूट ही होगा अभी, तो मैं देख रहा हूँ. नहीं, म्यूट नहीं हूँ.
हाँ हाँ
आप बताइए. हेलो.
सर आप. हाँ अभी आया आवाज, आगे अभी आ गया
आ गया आवाज. चलिए देखते हैं अब.
हाँ
लेट्स
सर.
लेट्स ट्राई इट. लेट्स ट्राई इट आउट. राइट.
यस.
राइट. आप बताइए. इज इट बेटर नाउ? Is it
या
better now?
ऑडियो इज बेटर.
Okay,
यस
okay.
यस.
All right. I don't know what's going on. All right. So where I was. All right. So let's start with this slide again. Okay. All right. Shall I go back to the previous slide because somebody have missed it, or shall I continue with this slide?
सर एक बार जस्ट शो द लास्ट स्लाइड.
All right. Yes.
यस, स्टार्ट फ्रॉम हियर सर.
Okay, right. All right. Now, look at this. This is a Cmos inverter, which is the most important block. Let's say starting block for. Oh, okay, okay. Hello, yes, yes. Hello. Yeah, yeah. Am I audible now? It's okay.
Yes, yeah, sir. You're audible.
All right.
Clear.
Okay, okay. I think there is a confusion. Now, what I'm saying is the important event that happens in a CMOS inverter is the charging and discharging of a load capacitance. So either the load capacitance is charged for a 0 to 1 transition, or it is discharged for a 1 to 0 transition. Now, So what really happens? Okay, sorry. So what really happens is the energy drawn for a 0 to 1 transition. Let's assume that I have a step input at VDD going from 0 to V, and then the this PMOS transistor I can modulate using a resistance, and then this. So it's a simple RC circuit. And I'm assuming this VDD as a step input 0 to VDD. Now I want to know how much energy is required to charge the load capacitance. So energy required will be drawn from the battery. So it will be like VDD is the supply voltage, and is the current through the capacitance is CV dV C by dt, and then dt. So this will be the energy will be power voltage into current to dt, and finally the voltage across the capacitance will be just V. So we have to integrate from 0 to V. So the energy required from the battery will come out to be CV, sorry, will come out to be CV square. So um, so the energy required will come out to be CV square. That is for every 0 to 1 transition, the energy which is extracted from the battery will be CV square. Now out of this, the energy stored will be half CV square on the capacitance, and definitely half CV square will be lost in the PMOS transistor. Now, this is what I covered. So you must understand that V will be VDD for a CMOS inverter. So for the 0 to 1 transition, the energy required will be CL, the load capacitance, into VDD square. Now, I'll go to the next slide and identify the different other components in CMOS in addition to this component. So this is one of the most important component, the energy required to charge and discharge the capacitance. Because normally in all digital circuits, we have to charge and discharge the capacitance. So let's move ahead. Yes. Again, there is a problem.
No, no,
Yes.
sir, not now.
Am I audible now?
Yes, sir, clearly, no problem now.
Okay. So that's what I'm just wondering. Now look at this. This slide shows the three different components, three different sources of power consumption in CMOS, and I'll take each of them separately. The first thing which I identified is the power required to charge and discharge the capacitance. That's the first component. I already told you it depends on the value of the load capacitance. It depends on the square of the supply voltage. It also depends on what is the probability of a 0 to 1 transition, because for every 0 to 1 transition, this energy will be consumed, and the energy consumed will be CLVDD square. So if the probability of 0 to 1 transition is 1, so for every transition, the energy will be CLVDD square. So we have to identify the three different components. If you really want to reduce this power, we have to reduce the load capacitance. The second option is we have to reduce the supply voltage, because this component is a very strong function of the supply voltage, VDD square. And we have to also reduce the probability of 0 to 1 transition. So if we can somehow reduce the activity in a circuit so as to reduce the probability of a 0 to 1 transition, then also the power goes down. Now, so these are the three important components, of this, what's called the dynamic power. So this is the first component or the first source of power dissipation in CMOS, which is CL VDD square in the probability of a 0 to 1 transition. Now, the second component of the power will come again when you extract the power from the supply voltage. Now, whenever you have a 0 to 1 transition at the input or a 1 to 0 transition, you'll come to know that, let us assume that if the input is VDD by 2, if I assume that the input is VDD by 2 in the middle, it's undergoing a transition. For VDD by 2 input, which is in the middle, both the NMOS transistor and the PMOS transistor will be on. That is, during transition around here, 0 to 1 or 1 to 0, both the PMOS and the NMOS transistor will be on at the same time. And therefore, during that transition, you have a direct path between supply and ground for a very short duration when both the transistors are on during transition. So this component of power is also the short circuit power consumption. And this also happens only during Of course, this also happens only during transition, where you have a 0 to 1 transition or a 1 to 0 transition. Again, during transition, this also happens. And therefore, these two components, the dynamic power component corresponding to charging and discharging of the load capacitance, and this component, which we call it a short circuit power, which I'm not going to discuss because this short circuit power component will be very, very low right now at the nano scale. So at the nano scale, when the supply voltage is around 1 volt or maybe 0.9 volt, and the threshold voltage is around maybe 0.2, 0.3 volts, then this transition region is very, very small, and therefore the short circuit power is negligible. So what we have today at the nanoscale, the major components are this dynamic power component, the component required for charging and discharging the load capacitance, and the last component here, which is the leakage power component. And what is the leakage power component? Today, the transistors are never off. As I told you in the sub-threshold, even when the gate to source voltage is zero, the NMOS transistor is on, is partially on. And therefore, some current always flows through the PMOS and the NMOS transistor. And that current is the leakage current. If I multiply the leakage current with the supply voltage, and of course, if I take the time, then that's also one energy. So this component is the leakage power component or the static power component. And this component will be active when things are not changing, when things are steady. When the inputs are at VDD and on ground, even then this power will be consumed all the time. And that's one of the biggest uses. So in reality, today, there are two major power components. This dynamic power component and the leakage power component. So what I'll cut it down. The leakage power is VDD into the I leakage, because leakage current is drawn from the supply voltage. Similarly, for every transition 0 to 1, if I'm operating F, the frequency F, now depending on if in the frequency, in the time period, you have a 0 to 1 transition, then that F01 is nothing but the probability of a 0 to 1 transition into the F clock. So if the probability of a 0 to 1 transition is 0, then this portion will be 0 and you don't get any dynamic power. So if there is no activity, the dynamic power goes down to 0. Now this portion, this short circuit power, because it's negligible, so I'm really not devoting time onto the short circuit power, especially the nanoscale, where the supply voltage has gone down. It has become very close to the threshold voltage, and therefore this portion, transition portion, has gone down, and therefore the value is negligible. Now, so remember always, so the two major portions of power consumption in CMOS is the dynamic power consumption and the leakage power consumption. And this I'll skip because this is not that important. Under dynamic, you also have a component which is glitching, which is also contributing a lot. And I'll talk about this glitching component while discussing it separately so that you can really appreciate. So short circuit power I have removed. Now what I'll do is I'll try to discuss this dynamic power in detail, and then I'll discuss the leakage power in detail so that you can appreciate how we can cut down the dynamic power and how we can cut down the leakage or the standby power or the static power. So let's try to move ahead and let us take up the dynamic power first. Now, this is like we have already discussed. The dynamic power depends on, look at this, the dynamic power depends on the load capacitance. If I take the power, the square of the supply voltage, and the probability of a 0 to 1 transition into the frequency. Now, this probability of a 0 to 1 transition, I can club it with the load capacitance and gives you a new name. We call it the effective capacitance. Effective capacitance of a MOS circuit is the activity factor, which is probability of a 0 to 1 transition, because 0 to 1 transition is the energy consuming transition, into the value of the load capacitance that you have in your design. So primarily, the dynamic power has three components. The first component is the effective capacitance, which is the product of the activity factor, the probability of a 0 to 1 transition into the load capacitance. It also depends on a very strong function of the supply voltage, VDD square, and the frequency. Now I can answer some of the questions that must be cropping up in your mind. How to cut down the dynamic power consumption in a CMOS. And I answers, which will be clear from the next slides, which is very, very broad answers. Remember, if the output voltage is not charging up to VDD, or maybe if it is charging up to some lower voltage where the swing is small, the VDD square has to be replaced by VDD into V swing. So if we, because if it is not going all the way to VDD, then the power consumed will go down. It will be VDD into V swing. Let's say if this is, I'm assuming this is, let's say 4 volts, and this is, let's say this is going only to 3 volts, then it won't be VDD square. It will be VDD into V swing. The swing is the maximum output voltage that you can have at the output 3 volts. So remember that forever. So let's start with the different components of the dynamic power. And I want your attention because this is a very important slide. Okay, so how we can cut down the dynamic power in a CMOS? What are the different ways of reducing it? The most important way, which I'll discuss first, is supply voltage scaling. That is the reason why nobody designs at 5 volt. The design voltage has gone down from 5 volt to 1 volt to cut down the chip power density. The most effective means of reducing the dynamic power is supply voltage scaling. So reduce the supply voltage from 5 volt to 1 volt, tomorrow maybe 0.9 volt, day after tomorrow maybe 0.8 volt. So supply voltage scaling is the trend. So the most effective weapon under the control of the designer is supply voltage scaling to cut down, as you will see, not only the dynamic power, but also the static power. And therefore, 5 volt is history today. And the trend is towards lower and lower supply voltage. The second most effective way is you can cut down the activity factor in your design by some ingenious means, and I'll talk about those means in my subsequent slides. What are the options available to cut down the activity factor? Of course, it's challenging, but we have to really find ways how we can reduce the activity factor of the design so that the dynamic power goes down. And then you have to do some sort of intelligent circuit design, reduce the circuit size, reduce the length, reduce the transfer dimensions, so as to reduce the load capacitance. If you can cut down the load capacitance, the dynamic power goes down. And then, of course, if you can do that, the frequency of operation, the dynamic power is a linear function of frequency. It goes up with frequency because higher frequency means more transitions, and more transitions means more dynamic power. And that is another reason why nobody is looking for a 10 gigahertz frequency just to contain the chip power density. The frequency is not rising beyond 3.5 gigahertz. And the era of multi-core has come primarily because the frequency is also directly related to the dynamic power. We are not able to get the required value of chip power density if we use a single processor and go on increasing its frequency. And the trend has now become multi-core just to solve this power problem. So now, out of this thing, the most important take is the most important weapon is supply voltage scaling, followed by activity factor, load capacitance, and frequency. Let's move ahead. And this slide shows that people realize that it's impossible to go with the 5 volt TTL compatibility, which has been going on for ages. And they realize it quite late. In 0.35 micron technology, they have chosen a voltage of 3.3 volts. And now the trend continues till today that supply voltage has to be scaled. And again, I've used the same formula for the ID on. The supply voltage is being scaled and scaled and scaled. Now, the problem with this is the drain current is going down and down if we don't do anything with the threshold voltage. If I don't do anything with the threshold voltage, what happens? The drain current goes down. If the drain current goes down, more time will be required to charge and discharge the capacitance, and therefore the delay will go up, and therefore the circuit will become slower. And that biggest casualty of the supply voltage scaling is the delay problem. So whenever you want to scale the supply voltage, you have to pay in terms of delay. The delay rises, and it's very clear from this expression. If you want to cut down the rise in delay, one option is to scale the threshold voltage proportionally so as to maintain VDD by VT. That is, if you scale the supply voltage, to reduce the dynamic power consumption, you have to also scale the threshold voltage proportionally so that the drain current remains constant or somehow maintained so that the delay will not be affected. Now, before taking up how you can really combat this problem in real architectures, supply voltage scaling giving you problems in your design, because when you scale the supply voltage, your timing problem will arise, the delay will go up, and therefore the frequency of operation will be affected. And how to overcome this problem? Now, I hope everybody is familiar with the critical path concept in a digital design. So I hope that you are all familiar. If not, I have put this slide for the people who are not familiar with the concept of what's called the critical path. Now, what is a critical path? The critical path is the longest path in your design. By now, I think, since I think maybe you have the VLSI background, now in a synchronous system, the longest path decides the frequency of operation. If there are thousands of millions of paths, the minimum path has no say. It's a worst case design. So all synchronous designs are worst case designs. The longest path decides the frequency of operation and not the shortest path. And therefore, in the critical path, the longest path will decide the frequency of operation, unfortunately. And therefore, that's the biggest challenge. So if you really want to speed up the design, you have to reduce the length of the critical path. Now, the problem is if I scale the supply voltage blindly, the critical path length will go up and therefore my frequency of operation will be affected. So that's a big challenge, how to maintain the critical path and still carry out supply voltage scaling. Now, so this is the slide I've already told you. When you scale the supply voltage, the delay will exponentially rise. So that's a big problem with what's called the supply voltage scaling. Now, so how you can overcome this problem? Now, there are few parts which are critical in your design. So what you could do is on critical paths at design time, I cannot use a lower supply voltage. So if you have a million paths, out of the million paths, maybe hundreds or 1,000 paths are on the critical path. So the transistors which are lying on the critical path, they must use high VDD, because I can't really afford to reduce the VDD of transistors which are lying on the critical path, because that will affect my throughput in a big way. Whereas a huge number of transistors are lying off critical path, which are not lying on my critical path. And for all those transistors, I can reduce the VDD. So now I'm getting the best of both worlds. That is lower VDD for transistors which are not lying on the critical path, higher VDD for transistors which are lying on the critical path. So now in today's design, you have multiple VDD. So this is the most important takeaway for low power design. If you really want to do low power design, just cannot reduce the voltage to a very low value, even for critical power transistors, because then your throughput requirement will never be met. I want to meet my throughput requirement is still reduce the supply voltage and hence the power consumption. And how we can do that on the critical path, don't disturb the supply voltage. Keep it at the required level so that your specs will be met. And off critical path, there's a huge number of transistors off critical path. For those transistors, you can use a lower supply voltage. So you get not only you are able to meet the specifications, but also you can reduce the power at the same time. So you can get the best of both worlds. So this is a strategy which has to be followed. So in a nutshell, what I say that a low power design is multiple VDD design. So today on a chip, you don't have a single supply voltage. You have multiple supply voltage, ideally two, because people have found that two is really the best possible way forward, because the multiple supply voltage will complicate things. So rather than have a lower supply voltage and a higher supply voltage, and that will be, and then you need a DC to DC converters to move from one supply domain to the other supply domain. And the reason why we are doing it, we want to get reasonable speed and reasonable power consumption. And that is a way forward for a low power chip. Now, so I think I'll skip the slides. And we have already put this, look at this, this is voltage scaling. And this slide shows that you have some chips in gray and some gates in gray and some gates in white. So normally, all the gray transistors, they are basically operating at lower supply voltage, and all the white transistors, they are operating at a higher supply voltage. And the white transistors, white gates are on the critical path, and that's why they're operating at higher supply voltage. And all the gray, they are off critical path, and there are various means available in the tools which will help you. So if there is a slack available, that is some time is available, the clock is arriving much earlier than required, then all the gates which are lying on those paths where you have a slack available in a clock, where you have time available, then those gates will operate at a lower supply voltage. Then those gates where the timing requirement is very stringent, you cannot further delay it, those gates will operate at a higher supply voltage, so that you can't afford to make them slower. And then you have to do the level conversion from one supply voltage to the other supply voltage at the boundaries without any problems. So you need these special designs if you want to get the best of both worlds. And now, these are, because I think I have limited time, so I'll have to skip the slides now. Now, activity factor, because the probability of 0 to 1 transitions will be different for different gates. For the static gates, people have found that they have a much lower activity factor compared to our dynamic gates. And therefore, although the dynamic gates have lower capacitance, because dynamic gates are much smaller compared to the static gates, but since their activity factor is very large, it's a big debate. Normally, dynamic circuits, they don't give you a big power advantage compared to static circuits. So remember that normally the dynamic gates, they are smaller, so you can assume that not only they are faster, but they also consume less power. But in general, the dynamic gates are not really great from a power point of view, because you need a clock for pre-charging, and the clock will consume a lot of power. Plus, the activity factor, the probability of a 0 to 1 transition in a dynamic gate is much larger compared to a static gate. Now, the concept of glitching is also very interesting. Glitching arrives because all the inputs, they don't arrive at the same time. So you have an A, B, C input. I have fed to a NOR gate, and then this will take some time. And A, B, and C, all the inputs will arrive at the same time. But then there is some time required to generate X. And because of this, because of the delay of this gate, some time is required for X to be stable, and hence momentarily the output Z will execute an I think an unwanted transition. This unwanted transition is the glitch. That is, since some time will go into for X to be stable, and A, B, and C arrives at the same time, and therefore since X will be available after a delay of a NOR gate, and hence uh, for the current value of X and C, you will get a glitch. So you get a glitch here. Now this glitch is the unwanted transition. And so what you need in a good design, all the inputs to all the gate should arrive at the same time. So how to overcome this delay? Then I think it must be guaranteed that C and X must arrive at the same time. If C and X are not arriving at the same time, because X is being delayed, why? Because A, B, C are at the same time, and you get an unnecessary transition in every transition, because this means glitch means a 0 to 1 and a 1 to 0. So every 0 to 1 transition is a power consuming transition. So these type of glitches should also be avoided. And I'll just give you a very interesting example to prove this. This is a very interesting architecture. Now you have this a comparator, and then you have two multiplexers and an adder. Now, if you look at this design, I can do it another way. I can put two adders and then a multiplexer. Now, if I try to compare the two architectures, 1 and 2, without glitches, this architecture, because it uses only one adder, consumes less power compared to this architecture. So it's 951 microwatts, let's say, any given technology. But if I include glitches also in my simulation, because this comparator generates a lot of glitches. So if you get a lot of glitches here on these two inputs, first then the number of glitches will build up here, and then lots of glitches here. So the power consumption of this design with glitches rises compared to a case because glitches are entering late here. in the last phase. So there's not a, and they are applicable only at the last multiplexers. These two inputs are glitch free because all the paths are balanced. And because the glitches are entering late, then this this will the with glitches the power is only 1357 microwatt, but in this the power is 1650 microwatt. So what I'm saying is you cannot ignore glitches. Glitches are unwanted spurious transitions because of unbalanced path in your design. So you must ensure, as a good design practice, all the inputs must be registered, all the outputs must also be registered, and all the inputs as far as possible should arrive at the same time. Otherwise there will be glitches and unnecessary transitions will consume power, because every 0 to 1 transition is nothing but an energy consuming transition. I'll skip the short circuit power because I told you already it's of less consequence. Now this is a very interesting slide. The supply voltage has to go down because of to cut down the dynamic power, because that's the strongest relationship between the dynamic power and the supply voltage, quadratic. So what is happening? If you really want to maintain the on current, the threshold voltage has to go down. But the problem is, if the threshold voltage has to go down, as I told you earlier, the sub-threshold leakage exponentially rises. So what is happening is the threshold voltage is reduced, and therefore the leakage power is rising, although the dynamic power is falling. So what is happening today? The dynamic power is falling, and because of the reduction in the threshold voltage, the leakage power is rising, or the static power is rising. And why it is happening? Because we want to scale the supply threshold voltage proportionally. If we want to avoid it, then the delay will rise. So that's the biggest challenge. So the second portion of the power consumption is what is called the leakage power or the static power consumption. Now, the subthreshold leakage. Now, when the VGS is less than VT, we assume that there is no channel. Of course, there's no channel between source and drain. But then you have N plus PN. Then the MOS transistor starts behaving like a bipolar transistors, and the current is not through drift, it is through diffusion, and therefore there's an exponential relationship between the drain current and the gate to source voltage. Now, so the biggest problem is there's an exponential relationship between the drain to source voltage and the threshold voltage. If we reduce the threshold voltage, the drain current exponentially rises. That is the biggest problem. And it also exponentially rises with temperature, and chip temperature is high. So you can yourself gauge the amount of leakage problem that we have because of the rising chip temperature that you have today. So that is a huge concern right now. Now, so how we can really overcome this leakage power problem? Now, gate leakage I'll not talk about, because gate leakage is negligible today, and the reason is the industry has already moved from a silicon dioxide dielectric to hafnium oxide, which is a much higher permittivity, and therefore the gate leakage is quite negligible. But I think it back now. Now this is like how we can really combat the leakage problem. Now, the leakage problem we can combat is, look, if I use a higher threshold voltage, the amount of leakage will be very small compared to a low threshold voltage. The amount of leakage will be very large. So that's a problem. Or we can come up with a nice transistor, which for this leakage also will have such a slope that it will make it zero. That is what we want. Company, and you can really become very rich. So think about coming up with a transistor with having a 10 millivolts per decade slope with all the other properties just like a CMOS. So that's a huge area to be in. Now the problem. Let us try to understand the problem and how we can overcome the problem. So if we reduce VT, the problem is the subthreshold leakage exponentially rises, but reducing VT decreases the gate delay. Now what we want the best of both worlds. We want low leakage power, as well as we don't want to sacrifice speed, because if we can't reduce VT, then my I on current will go down. So again, we have a strategy for it. Determine the critical paths at design time, and you, because critical paths are critical from a design perspective. I think I'll just wind up this and then I'll stop and take a 10 minutes break. Determine critical paths at design time and use low VT devices on transistors which are lying on the path, whereas high VT transistors are used for leakage control. That is, transistors which are lying on the critical path, which are time sensitive, we have to continue using low VT. We can sacrifice leakage on those paths, but the huge number of transistors which are not lying on the critical path, and those transistors we can have higher VT. So today, from a low power design, you must have a provision of providing multiple VT for a design, just like you have multiple threshold, multiple supply voltage to combat static power consumption. The greatest thing you can do is there has to be a provision of multiple threshold voltage. That is, rather than one threshold voltage, you can have multiple threshold voltage to combat the leakage problem. So what I'll do is, it's already 11:49. So this is the last slide which I really want to do. Now, what I'm doing here, again, there are white gates and again there are gray gates. So depending on the gates which are lying on the critical path, I can, or those gates are lying on the critical path, they 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 continue to be having a low threshold voltage, whereas gates which are not lying on the critical path, they have a high VT, and high VT means that their leakage can be controlled. And again, of course, I don't need any level converters, but I need, in a design, there has to be a provision of what's called multiple threshold, so that MOS transistors can have a multiple threshold voltage support. That's very, very important for the leakage perspective. What I'll do is, it's already 11:49, so I think it's a long way out. So I can stop here for 11 minutes, or so that we can again come back at 12 o'clock. Is that okay?
Yes, sir.
Because I think it's a long haul, and the remaining portion, I'll cover the basic actual architectures and ultra low power techniques in the remaining time that I'm having. So shall I come back at 12? Is that okay?
Yes, yes, sir. Yes.
Okay, I'll stop here and I'll continue from here. Thank you. Shall I start or?
Yes, sir.
Okay. Yeah, hello. Are the slides visible now?
Yes, sir. Slides
And
visible. Audio is also clear.
okay, sir. Okay. Now, what I'll do is, as a very quick recap, you do supply voltage scaling to cut down the dynamic power, and by doing supply voltage scaling, the delay will be affected. So what you do is, on the critical path, you use a higher supply voltage, and on non-critical path, you use a lower supply voltage. Now, to combat static power, you have to use a higher threshold voltage. But if you use a higher threshold voltage, then the delay will be affected. And therefore, on the critical path, you use low threshold voltage, and a non-critical path, you use higher threshold voltage. So basically, low power design is multiple VDD design and multiple threshold design to get the best of the power as well as the throughput. Now, in order to combat this static power consumption, there is one very effective technique, and that we call it a stack effect. And a stack effect is present when the transistors are in series. So this is an example of a two input NAND gate. Now, if the two transistors are in series, then what really happens is, if I ensure that this input is zero, let's say if this input is zero and this input is also zero under static conditions, then what really happens is, because of the leakage current, this will acquire some voltage here. Uh, and because of the body effect, the threshold voltage of this transistor will rise, and moreover, the gate to source of, voltage of this transistor will be negligible. Sorry, will be negative. And since the gate to source voltage of this transistor will be negative, the current through this series arrangement will be very small, and this transistor B will also be forced to carry the same current. Now, so if you have transistors in series and you ensure that the inputs are 0 0, under the standby condition, then it's possible to cut down the leakage by a massive value. So stack effect is one of the most important technique that is available in the hand of the designer to cut down the leakage current. And this you can get even at lower threshold voltage, the leakage can be controlled. So if I have a complex gate having a lot of transistors in series, it's good from the leakage perspective. Even for complex gate, because normally we prefer smaller gates for performance. So complex gate is also good for energy because then the interconnect capacitance really goes down. So complex gate gives you a much better value of the I-on-I-off ratio, especially on the non-critical paths. And this you can employ to cut down the energy as well as the static power consumption. Now, what is a general strategy? Because we have now talked about how to cut down the dynamic power. We have talked about how to cut down the static power. Now, what is a general strategy for low power design? Now, one strategy is, uh, in general, we don't want the best performance under all conditions. Some applications will tolerate, okay, I want to meet this specification. Let's say my design is operating I want to operate my design at 100 megahertz. There's no big advantage if I go beyond 100 megahertz. But whatever I have done the designing, that design is capable of operating at 1 gigahertz. So I don't want my design to operate 1 gigahertz. What I'll do is I will do supply voltage scaling of a 1 gigahertz design, so that now, rather than operating at 1 gigahertz, that design is forced to operate at 100 megahertz. And by doing supply voltage scaling for that design, is operating at 1 gigahertz under higher supply voltage. By doing supply voltage scaling, what we have done is we have we are forcing the design to operate at 100 megahertz, and by doing that, we are giving a big gain of in power reduction. So the excess performance can be used for power reduction. So this is the mantra. If you really want, for some applications, if the throughput requirements are not that stringent, you have to meet the requirement only, then you achieve better performance and then do supply voltage scaling to cut down the power consumption effectively. And I'll give you a very quick example. Let's say this is a uniprocessor architecture. We have just two registers and a function, a very simple explanation. And let's assume that the power consumed by this arrangement is this C reference, B reference square. Now what I can do is I can do either pipelining or parallel processing to speed up this. So one option is carry out the pipelining. Now let's say if I put one registers in between, the delay of this will go down from T sample to T sample by 2, so that now I can operate these at twice the F sample. But I don't want to do that. I don't want to do that because now this delay has gone up from a T sample, which is the time corresponding to F sample, to now T sample by 2. But what I have done is I have inserted one additional register. So now my delay has gone down to 2 sample by 2, but I still want that the same design will operate at F sample. Why I have done pipelining? I want to speed up this design. So now this design is capable of operating as twice the F sample because my delay has gone down for T sample, 2 sample by 2, but I won't do it. I will force this design to operate at F sample. So what I'll do is I'll do supply voltage scaling of this design till its delay goes up from F sample to T sample. And what I have noticed that by doing that, I've been able to cut down the supply voltage from let's say 1 volt to 0.58 volts. By doing that, I have now increased the delay because you all know that if the supply voltage goes down, the delay goes up. So now I have forced the supply voltage to go down and therefore the delay will go up. And so what I've done, you speed up the design through pipelining and then use supply voltage scaling to again get the required value of delay because there's no point in speeding up beyond F sample. My requirement was F sample. So I have done pipelining to speed up the design and then use supply voltage scaling to bring its speed back to T sample. And therefore, by doing that, supply voltage has gone down. The frequency will remain F sample or F reference. By doing this, for a pipeline design, the power is just 0.39. Look, it's a very interesting way of doing it. You speed up and then apply supply voltage scaling to cut down the power consumption. And similarly, you can do the same thing. You parallelize it, make the speed faster, although you don't want to do it. Why you are doing it? Cut down the power consumption. And here, of course, there'll be more capacitance overhead because of the pipe because I'm using two identical blocks. But then again, I've been able to scale the frequency down and then I'm getting some speed up, but then the area requirement will go up. So either you can use pipelining or you can use parallel processing. You speed up the design, don't increase the clock frequency. Then apply supply voltage scaling, bring the design back to the required critical path length. But by doing that, now you're operating the design at a reduced supply voltage and then you are getting the benefit of power. So you are able to meet the specification and reduce the power of the design at the same time. This is a very standard technique for low power design. Now I told you already, multi-core is good because you are not increasing the frequency. What you're increasing is the number of cores, and increase in frequency is a big nuisance because it directly increases the power consumption. Matching computation and architecture. So if I just want to implement this function, I can do it in a traditional way of ALU. But then what people have noticed is this is not the right way. If you can do it directly, you implement it hardware through spatial programming. It's a much better way from the energy perspective, also, of course, compared to this. So this is you match the computation with the architecture. So in general, the energy efficiency goes up if there's a strong matching between the architecture and whatever you want to compute, rather than doing it in an iterative fashion. This is not energy efficient because what people have found it the correlation becomes very poor between the data, and then there'll be a lot of switching if you do if you implement it the way it has been done in a traditional ALU. Now this is again very interesting. You can do this computation in two different ways. You have two adders, and I want to do it in two different ways. These two are absolutely identical. Now the advantage of this scheme is the inputs are correlated to this adder. That is, You know that if the inputs are correlated, means then the amount of activity or 0 to 1 transition goes down. Here what I'm doing, the two same inputs I am feeding to the adder, but they are basically shifted by different ways. One shifted by 8 times, another shifted by same time. So the inputs are identical, more identical to the adder compared to this. Here you have a normal input, and then this will be shifted by 7 bits. So now the two are becomes radically different compared to one input shifted by 8 and another input shifted by 7. So they are more correlated compared to this. And then you feed the input here, and then so what people have found that, look at this, the sum one transition probability in this in this arrangement, the number of bit switching is much lower compared to the number of bit switching, and the probability here is much larger. So 30% reduction in switch in signal activity if you move uh, from here to there. Now, why? What is the big advantage? You have just shifted the inputs from one adder to the other adder, and then the number of activity factor goes down. So in your design, you have to ensure that the inputs are correlated. That is, there'll be less transitions, but most likely that is, the input should be similar. If the inputs are similar, then the adder might you're able to reduce the activity factor inside the adder, and therefore this correlation of the inputs is very important. That will also help in reducing the power consumption. This I'll remove. This I think I can skip. Now, what are the different techniques? I'll just summarize very quickly. For the dynamic power and the static power, multiple supply voltage option for the dynamic, very important. Multiple threshold for the static. Transistor sizing to speed up the design, and then up supply voltage scaling. Reduce the activity factor, reduce the capacitance, no glitching, and use complex gates because they're more energy efficient in general compared to smaller gates which are faster but they consume more energy. Transistor stacking, I told you already, it is good for static power consumption because if you have transistors in series, then because of the body effect and the negative VGS, the threshold voltage goes down. Longer length transistors will give you higher threshold voltage and then more less leakage. Lower supply voltage will reduce leakage because the leakage power is VDD into I leakage. So it's a very important technique. And of course, complex gates will have more stacking, more transistors in series, and therefore less leakage. I think I'll just, what are the general guidelines? You do concurrency and pipelining. That's very important. In your design, make the design faster, and then you bank on what's called supply voltage scaling or maybe frequency scaling, because supply voltage scaling is the most effective weapon under the control of designer to cut down the dynamic power. And then you have to match the algorithm with the architecture. I told you already, there has to be a good matching between the algorithm and the architecture if you really want to get energy efficient result. Then locality of reference. This is like a cache-based architecture because I'll show in some of the few slides that if you have an FFT architecture where the data is always located in a small memory because of locality, although a traditional FFT is highly consuming in terms of power consumption because the data it has to be grabbed from all the points at the same time. There's no locality of reference, but if you can modify the FFT algorithm and have sort of some of a locality of reference where you can use a small memory to store the information all the time, then that will be very effective from the power perspective because you are dealing with data, you're bringing information from a point which is nearby, and therefore the capacitance goes down, and hence the energy also goes down. You have to have a high correlation because if there is a high correlations uh, through maybe ordering of the way you process the information, then if the correlation level will be higher, the amount of transition goes down, and hence, of course, the power goes down. Uh, Optimum topology has to be chosen. That's very obvious. And then, of course, the word length, because you see which word length has to be chosen. It's not necessary that all the word length should be identical. You have to choose very judiciously the word length so as to minimize you have to minimize the word length so as to keep the errors within limits and still do the job. So that because the word length increment also will increase the power consumption in a big way. Now, without really further delay, I'll just highlight the important contributors to power. And this slide shows the breakup of power for microprocessor and FPGA and a signal processor. On the FPGA, it's clear because the interconnect will consume a huge power. 40% of microprocessor goes into clock because clock goes everywhere. It switches a lot. So there must be a mechanism to cut down the clock power. It's a big nuisance. And the problem with the interconnect is we are able to scale the capacitance of the transistors much more effectively compared to the interconnect capacitance. So interconnect resistance and capacitance is a much bigger nuisance at the nanoscale compared to the transistor. And therefore, the interconnect power is rising, the clock power is rising, and we have to have some innovative techniques to cut down the interconnect power and the clock power. What we can do, we have to have a lower capacitance in the buses somehow. The swings should be smaller, and we should have a lower activity. Maybe 3D ICs is the way forward because then the interconnection length will go down. You have to look for novel materials where the permittivity is very low so as to cut down the capacitance. And maybe we can explore what's called the OSI model rather than the bus architecture, especially if you have a huge number of processors on the chip so that they can effectively communicate without any problem. And some people are talking about what's called the optical networks as well. Now, there is another very interesting technique. I really don't have that time to discuss it, which is really your what's called the bus invert coding. That is the details. I'll give you a very basic idea. What's bus invert coding? Normally, we want data to be highly correlated on the bus. That is, if I have some value X going on the bus, the value which is available after X in the next time slot should have a high correlation between X and Y and Z. If the values are highly correlated, then the number of transitions on the bus goes down. And remember, the bus is high capacitance. If we are able to reduce the transition activity on the bus, the power will be dramatically reduced. So bus invert coding ensures that if the number of bits between the current bus value and the next bus value is more than let's say n by 2, if n is the bus width length, then it inverts the value so that now there'll be a more correlation between the current value and the next value. So basically, bus invert coding is a very simple technique to increase the level of correlation between the current value and the next value on the bus. And this helps in reducing the bus power by around 25% for random data. Now, how we can cut down the clock power? Clock goes everywhere on asynchronous design. It's a nuisance. We have to can switch to asynchronous, but then asynchronous has so many other problems as well. Now, how we can cut down the clock power? One way is reduce clock swing, which is not really, you cannot pursue. Another thing is remove go asynchronous. It has many problems. As I'll highlight you maybe in one of the slides, what are the problems with asynchronous where you don't have a global clock. But then the trend is in that direction. GAN, globally asynchronous, locally synchronous, because you cannot maintain clock skew on a big chip today because the frequency has risen, the chip size is bigger. You cannot ensure that all the clocks will arrive at the same time. So the mantra today is you have maybe globally you can think about asynchronous and locally you can have synchronous. And then, of course, as I told you already, you can think about an optical clock network. So clock is one of the biggest nuisance from the power perspective. And there are various techniques which are available to cut down the clock. Something asynchronous, partially synchronous. And these are the way forward. But still, there's no clear answers as far as the clock power is concerned, especially in the standby mode, we can remove the clock through clock gating, as I'll be telling you shortly. But then when the power is on, the clock is one of the biggest nuisance of power in synchronous design. Now, memory is 50 to 90% today in any advanced chip, especially this SRAM, and it's one of the most power-consuming block. Normally, the problem is we have to do all the techniques like multiple VTH, multiple supply voltage. 6 transistor SRAM is a big nuisance. We have to come up with some innovative cells are available, 9 transistors, 8 transistors. Maybe we have to use complex chips to cut down the SRAM power because this is one of the biggest contributor of static power because you cannot remove the supply even when things are not active, because SRAM stores information. At least the minimum voltage has to be maintained. Now we are hoping that the magnetic RAM, which is non-volatile, will be able to solve this problem. But till MRAM becomes absolutely commercial in terms of the pricing, we have to wait. But MRAM holds a lot of promise, magnetic RAMs, which really have all the good attributes and is capable of, especially in the IoT setup, where SRAM is one of the major contributor of power, that MRAM has a good potential to replace the SRAM there, because then there's no need, we can power it off without any problem in the sleep mode, and there is no need to retain the information in the form of data because it's non-volatile. Now, the second area is like dynamic power, static power at the same time. Now, the second is the standby. When things are not switching, when mobile phone is inactive, what are the options on the table? For dynamic power, the most important option is you prevent the clock from going to the modules. That is clock gating. Clock gating is one of the most effective technique to cut down the standby power. When things are not switching, you should prevent the clock to go to the various modules. If you can do that, the clock power will go away. And that's one of the most effective technique to cut down the dynamic power in the standby mode. So once you are able to cut down the dynamic power in the standby mode, what are the options for the static power? You power gate. Power gate means you remove the supply voltage when things are not active. Power gating, you power gate the supply voltage. So I'll tell you how to do it. Then you body bias, that is, you do body biasing by increasing the threshold voltage of the unused transistors which are not active. And by doing that, the threshold voltage rises and therefore the leakage power goes down. And then, of course, supply ramping is one of the same technique like power gating. You just reduce the supply voltage to any level. Depend for the memory, you have to do it so as that the memory should retain the information. But for all the logic power, you can bring it down to zero. So for dynamic power, it's clock gating, and for static power, it's power gating, body biasing, or supply ramping. Let's say how you can do the clock gating. Now, clock gating is a very simple one. When things are inactive, you put the enable equal to 0, and therefore the clock will be prevented from going to the registers. And all the registers output will remain stable, and therefore in this logic module, things also will not change at all. And then you put all these transistors in the high VT mode by doing body biasing. Now you ensure that this enable is 0 means this inputs to the logic modules is not going to change as well. So the clock gating is the most effective technique for cutting down the dynamic power through the different enable signals when things are not active. Now I told you already the body biasing can control the threshold voltage, and body biasing can be very effectively employed when things are not active. You change the body bias of all the transistors so that all the transistors now will have a high threshold voltage. So this body biasing is a very effective technique when things are inactive, so that all the transistors threshold voltage will be raised, and hence the leakage power goes down. Power gating, for power gating, I think you need some extra transistors, like you need this transistor with a high VT, and then you need this, we call it a header or a footer transistor, these two transistors, and then you have a logic with a low VT. Now, this logic will work fine under normal circumstances, but what happens is when this logic is idle, then this will be a lot leaky. So now I have put a high VT transistors in series. Now, when the high VT transistor is in series, the leakage through this transistor will be very, very low, and therefore, when this transistor is off, there is no leakage through this transistor. When the leak, because it has a higher VT, and once it has a higher VT, then power gating can be employed to cut down the power consumption. I think supply voltage damping again is the same thing, where you just move the supply voltage up and down during the standby mode, and by doing that, you cut down the standby power. Now, runtime is runtime means when the processor is active. At times, the processor is having higher load. At other times, the processor is having a lower load. Now, when the processor is having a higher load, you need higher voltage. When the processor is having a lower load, you need lower voltage. The throughput requirement is less. Similarly, the frequency requirement can also be changed. Now, so what is how you can do what's called the runtime optimization. Now, runtime optimization, I'll show you a very interesting slide. Now, if I have this module, now this is a self-adaptive system. Now, in a runtime scenario, you should be able to dynamically adjust the supply voltage and the body bias. Supply voltage for controlling the supply voltage of the design, and body bias for controlling the threshold voltage. Now, for this to work fine, you must have a lot of sensors for temperature. You must have a lot of sensors for leakage. You must have a lot of sensors for delay and activity. All these values are monitors on a chip. And these values will go to a controller, and then the controller will decide what is the most effective value of the supply voltage and the body bias, which must be applied to the different modules of the chip. So this is a purely adaptive system. That is, now you are controlling the supply voltage and the threshold voltage in a dynamic fashion, depending on the values of the leakage, temperature, delay, and activity in real time. And if you can do that, you can create a very fantastic system. But then it requires loads of sensors, and it's effective if the module load is changing all the time. So in a nutshell, in the runtime, I can use what's called dynamic supply voltage scaling, dynamic frequency scaling, and variable threshold voltage to control dynamic power and leakage. But then I need loads of sensors um, to do it. Um, for for standby power active, I can reduce by clock gating, and leakage power I can use by putting sleep transistors, power gating, and body biasing. And at design times, I've already discussed the technique. So this is like a summary of whatever I have covered till now. What are the different design time techniques? What are the different standby technique? And in runtime, what are the different options available? Now I'll just move on to a very short things about. It's already 12:30. A very short thing about what's called the ultra low power design area, which is very upcoming, especially in the IoT node. In this area, we don't bother about the throughput. Throughput can be kilohertz or maybe a lower megahertz. So the whole idea is by how much we can reduce the supply voltage of our design so that we have to just meet the spec. The real goal is low power, ultra low power design means ultra low voltage design. So before that, before taking up, let's find out, let's try to understand this is CMOS inverter output characteristics up to which voltage it can work fine. Now, as you'll come to know that till I think lower than 100 millivolts, the characteristics remain the same. You'll be surprised. The threshold voltage is fixed for all the designs, and your inverter is working fine even below 100 millivolts. So now there's a lot of scope of cutting down the power consumption, the supply voltage. That is, the inverter can operate at 100 millivolts. Now I have to find out what's the minimum voltage. Now minimum voltage is the thermal voltage. You all know is of an electron is like is kT by Q. It's around 26 millivolts. So if you want the electrons to really move, we need a higher voltage than that. So a typical minimum supply voltage of an inverter people have found is around 48 millivolts. Uh, for a PMOS and MOS ratio of around 1.5 when the two are symmetrical. But in reality, we need around 100 millivolts. So there's a lot of scope we can cut down now. So we can design useful circuits by using a supply voltage lower than the threshold voltage. That is, now we are using this subthreshold region for creating useful circuits, not only analog circuits but also digital circuits. So this is an example to show you is the people have designed a subthreshold FFT processor operating at 0.18 micron supply voltage with the supply voltage of varying from 180 to 900 millivolts and the clock frequency varying from 164 hertz to 6 megahertz. At 0.35 volt, the energy is 155 nanojoules. Perfect. So look at this, the clock frequency is like 10 kilohertz. So at 10 kilohertz clock frequency, the energy is just like 155 nanojoules. So and the processor is 1024.16.FFT. So the point is that at VDD around 350 millivolts, we are operating in the subthreshold region, and the energy really goes down to 155 nanojoules. So for ultra low power design, especially in the IoT scenario, where energy is the number one priority, we can ensure that the chip operates in the subthreshold region, even below the threshold voltage. And by doing that, the overall energy goes down dramatically. Now, the big challenges are at lower voltage. The big problem is there is the delay is very high because we are not. So what we gain in energy, we lose in delay. The throughput is dramatically affected. Moreover, there's an exponential relationship between the drain current and the gate to source voltage. So the variability is very high, poor variability. And that's why the current trend is we don't want to really operate in the subthreshold region. We can sacrifice some energy for performance and move to what's called the near threshold region, especially at the nanoscale where the transfer become highly variable. So near threshold is the current trend, which will give you the best of both worlds. Will give you energy. You have to sacrifice energy, but then the performance goes up by a huge margin. And maybe that sort of performance you need if you want the AIs to go into the IoT nodes, because kilohertz will not give you that sort of performance. So the trend is like slightly better performance the IoT node, a near threshold where it can sacrifice a bit of energy, but then we gain a huge amount of performance by that. And then, of course, the hunt for the novel devices with the steep subthreshold slope will continue. Let's say an ideal switch. That's the solution. Now, so the last leg is I have around 45 minutes, and I'll try to cover up some of the low power DSP architectures to do justice to what the whole thing is all about. Um, Now, again, the techniques remain the same. You cut down the memory power, you cut down the clock power, you cut down the power at design time, you cut down the power at standby time, you cut down the power at runtime, and the techniques remain the same. Multiple supply voltage, multiple threshold voltage, and the different small techniques which are available for low power. And you can do it at all possible levels of abstraction. Now, I'll tell you some of the important things because with the limited time I'm having. Now, if I really want to implement an algorithm, the best improvement you get is at the algorithm. If you can tweak the algorithm so that it requires minimum number of operations, it requires minimum memory, so that is you can get the massive improvement. And then of course you can think about the architecture. You can do pipelining and then parallel processing, speeding up the design, meeting the throughput, and then do supply voltage scaling. Or you can do circuit improvement. Circuit improvement will not give you much improvement. It's 10 to 30%. So the real improvement lies at the architecture and the algorithmic level. That has to be kept in mind. Uh, this is just for your understanding. For a simple addition thing, you can use a single adder, or you can use a parallel architecture, or you can use a parallel and pipeline architecture. For a simple algorithm, you can have multiple solutions. And which solution to choose is, I told you already, concurrency gives you a lot of leverage in terms of power consumption, because then you can do supply voltage scaling and do a lot of reduce the power in a massive way. There are some designs which are like this is a very simple design problem, which shows that you can do it like this is a polynomial calculations. It seems that you cannot parallelize it. So like this algorithm, if you write it in this form, it seems that first of all you have to compute this expression, only then you can compute this expression, and then this goes on. Like this has to be iterative. So you cannot parallelize it. But then you can rewrite the same expression in a different form. If you can write the same expression in a different form, it is possible to carry out the parallelization. So what the message is, given a problem, you have to do lots of mathematical transformation so that for the same algorithm, you can come up with an architecture which gives you low power. And the maximum benefit will be when you tweak the algorithm so that it gives you the best architecture in terms of the resources, in terms of the memory, in terms of the data path. Uh, so I'll just skip this. Now, this is a typical DSP system. Normally, in a DSP, you are getting the data all the time, and you have to carry out the so you sample the information and do it. So basically, you have to process the information at the sampling rate. So there's no big advantage once the sampling requirement is met by the hardware. There's no big advantage in making the computation faster. What you have to do is you have to just meet the sampling requirement. There's no point in going beyond the sampling requirement for a given specifications. And then you can speed up and then do supply voltage scaling to meet the sampling requirement, as I already told you. I don't want to go into the details. I'll tell you some of the simple techniques. What are the different techniques? Again, the same techniques are applicable to DSP as well as communications and all areas, but then I'll highlight some of the interesting techniques which are available in the DSP world. First is operation reduction, and I'll talk about it. Second is you can carry out the ordering of the operation. That is, you do it in a particular order so as to have a high correlation. And I'll give you examples of it. Then you carry out substitution, because multiplication is one of the most power consuming operation in the DSP world. So if you can replace multiplication by shifting and addition, then of course you'll get in terms of benefit in terms of power. Block processing, again, this is a very interesting technique. This block processing, if you process in blocks, and by doing that sort of block processing, you're able to increase the level of correlation, then the activity factor goes down. Similarly, you can do some sort of sharing. Sharing also helps. That is, in a sharing multiplier, one portion of the multiplier is shared among all the shifters and adders. And I'll tell you about this sharing multiplier and how does it really help in reducing the hardware of an FIR filter. Then the importance of representation. It's also very important. Which data representation to choose from? Some of the data representation will give you benefit in terms of, let's say if I have a multiplier, if I have an operands which gives you more zeros, then I don't really have to do the multiplications. So the data representation is also very important. It has to be done properly. Now, word length reduction, of course, is very important. You have to choose just the right word length to meet the specifications. And then logic styles, synchronous and asynchronous, and then the cache-based architecture. This is a really interesting thing. I don't have the time to go into the details, but I'll tell you, the FFT algorithm was modified because in reality, the FFT algorithm is not good from a cache perspective because the data has to be fetched from all places, from all the points. But then it's possible to modify the FFT algorithm so that now the locality of reference is maintained and you can come up with a new architecture which is based on cache. And you know that if the memory size is small, it consumes much lower power compared to if the data is fetched from a big memory all the time. And this architecture is much more energy efficient compared to a normal FFT architecture, which is really a cache-based one. And then a very interesting area about what's called approximate computing, where approximation or accuracy is traded for reducing the power consumption. And this area I will also introduce because this is something very, very interesting as well. So let's move ahead and try to do justice to this. Reduce the operation reduction. Look at this. The operation is same, x squared plus ax plus b. You can use two multipliers here and then two adders, or you can just rejig it and used only two adders and one multiplier. So this is much better because we are able to save a multiplier. And if you're able to maintain the critical path, it's the best. So operation reduction also helps. The same thing, you can just modify the expression, do the transformation to cut down the hardware. That helps without disturbing the critical path. Now, this is a direct form FIR filter, and I'll try to give you some of the examples based on the direct form, how these we can come up with a low power architecture for this. Now, this is like I have proposed some of the single ALU solutions for this, especially for hearing aid applications. Now, you need because the coefficients are fixed. This is one big plus of this. It's not an adaptive filter. The coefficients is fixed, and we can exploit these characteristics to do some sort of low power design for the direct form FIR filter. So you need the the RAM to store the data, and then the ROM to store the fixed coefficient, and these are the registers, and then you have to feed it to the arithmetic block having the multiplier followed by an adder. This is the block. So this is the basic structure, and you do it iteratively to compute this. This is because there's only one multiplier present in the design, and this is for a hearing aid application. Now, how you can cut down the power of this DSP FIR filter? Now, the most power consuming element in this happens to be the multiplier, especially for the lower size filter. So this is one of the main contributor of this power consumption. And how we can lead. Now the big advantage is the data is variable. Of course, we cannot control the data, but the coefficient is fixed. Now we have to because since this is the multiplier is the most power consuming block, we can reduce the activity inside the multiplier by reducing the activity of the coefficient. That is, rather than multiplication in a specific order, we can alter the multiplication sequence so that the activity factor between the successive coefficient which we are feeding goes down. So if we can reduce or we can increase the correlation of within the different coefficients which are feeding to the multiplier, then the multiplier activity goes down, and therefore the power consumed by the multiplier goes down. So this is the basic signal flow graph. So this is one of the ways of reducing the power consumption of the FIR core, that by ordering the coefficient rather than this first of all putting H naught, H1, H2, that we can alter the order of S0, H1, H2 the way we are feeding it, so that the activity factor between H naught and the next H will be reduced, and by doing that the power consumption of the multiplier goes down. Now, the same thing we have tried out in the FFT processor, that is 26 It has got the butterfly structure. Now, if you look at the last stage of this, and these are the fixed coefficients of the FFT, and all the coefficients are changing like 0, 1, 2, 3, 4, 5, 6. And we have to feed these coefficients to these are fixed factors or fixed weights, which has to be fed to a complex multiplier. Now, the whole agenda is, again, we have to, the sequence of this, rather than first of all 0, 1, 2, 3, 4, 5, 6, 7, rather than following this specific order, why not put it in a particular order so that the activity factor between the different coefficient goes down. And by doing that, we can cut down the power of a complex multiplier, because a complex multiplier has got around 4 real multipliers. So this complex multiplier is also one of the major power consuming of a block of the FFT. And by doing the ordering of the fixed coefficients, we are able to reduce the activity factor inside the multiplier. And once the activity factor inside the multiplier goes down, then the power consumption of the multiplier also goes down. So this shows that the different coefficients of a multiplier, the real and the imaginary coefficient. Now, rather than so what we have done it, rather than in feeding it in this particular order, we are feeding it in a different order. Now, by feeding it in this order, if we do that, now look at the advantage. Now these two coefficients are same, no switching. 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 So what we have done is we have ordered the coefficient in such a way that the activity factor between the successive coefficients fed to the multiplier goes down, and by doing that, the power consumption goes down. So I think when we have done it, it's possible. It's very clear that the activity factor goes down from because reduction is around 60-70% we have achieved compared to the normal way of doing things. So for a different FFT size. Now, so this is one of the interesting way of, that is, rather than giving in a particular order, you carry out the reordering so as to reduce the Hamming distance between the successive coefficients, because the coefficients are fixed, they are known in the FIR filter as well as in the FFT processor. So wherever I have a multiplier having fixed coefficients, I can carry out the reordering technique. And by doing the reordering, we ensure that the successive coefficients are strongly related. And by doing that, the activity factor goes down, and hence the multiplier power goes down. So by doing that, we have been able to reduce the power saving in the single butterfly FFT processor by a big way. Of course, since we are targeting only the multiplier, the power saving goes down for a bigger and bigger FFTs, because only the multiplier power goes down, the other power remains unchanged. And since a bigger FFT will have more memory and more other blocks, so the percentage power saving goes down as the FFT size becomes bigger. We have extended it also to the pipeline FFTs. The same ordering techniques, although it's very difficult for the pipeline, but we have managed, because of the pipeline FFT, you have to change the data sequence also if you are changing the coefficient sequence. But we have extended it for the first time for the pipeline FFT, and we have got some reasonable results for the because I think it's for I think 15 to 20% we get for 64 point FFT. Even thing which you can do for the multiplier is you can do what is called, because the coefficient for FFT and FIR is fixed, they're not changing. You know the coefficient. So what you can do is a multiplier, you can replace it by a reduced multiplier and shifter. For instance, this is a very simple example of an FIR filter. You have these coefficients, let's say, of a 10 tap FIR filter. Now, this is the corresponding to complement representation, which is the popular representation for the fixed point DSP. Now, rather than using 8 bits for this, now a decomposed coefficient where -97 I can assume it is -128 plus 31 will also give me and -128 is in power of 2, so I can take the shifter will take care of it. -15 is like 2 to the power -16 plus 1. Similarly, so you can I can have this sort of representation, a reduced this goes to the multiplier, but now in this only the MSB bits are not changing at all. So this goes to the multiplier, but then the other portion goes to a shifter, and by combining this and the shifter, the activity here goes down dramatically compared to this. So I'm using a reduced multiplier plus a shifter to cut down the activity factor inside this multiplier. And by doing that, again, the activity factor goes down, and therefore, so what I have done, previously I have ordered the coefficients so that the activity factor between successive coefficient is very low. And if one input has lower activity, hopefully what happens is the multiplier activity goes down. In the second case, I have reduced the, I have taken the help of a shifter plus a reduced multiplier coefficient operand, and by doing that, this activity on the coefficient goes down. So because I'm taking the help of a shifter, all the two values, because -97 I have put as -128 plus 31, and similarly 93 I can also choose, and in powers of 2 plus another is very interesting technique that's called block processing. This is an FIR filter values, y0, y1, y2, and this compute like x0, h1, x -1. Now this is again a very interesting technique for a single multiplier architecture. Now look at this. If you try to compute the values, if you just follow a normal sequence, both the values are changing, x0, h0. Both the values are changing. After that, x -1, h1, x -2, h2. So if I compute the values in this particular sequence, first x0, h1, then x -1, h1, then x -2, h2, then x -3, h3, both the input x and the coefficient h, they are changing at the multiplier. But if I process in block, if I process these two values simultaneously, y0 and y1, then let's say what is the advantage? If I start processing from this side, let's say what is the advantage? Log 0. Now if I start processing on the extreme right, the big advantage is when I compute this value first and then compute this value next. Now these two values are same. No activity on this, 0 activity. I'm able to hold h3 constant, the coefficient h3 constant for 2 clock cycles. That is here as well as for here. So the activity goes down on the coefficient input h3. Now, if after this I go there, then look at this, x -2, and here also x -2. Now x -2 is not changing, although I'm changing h3 with h2, but the data is not changing. If I compute this first, then I compute this second, and then if I compute this third, now here I'm able to maintain the data input. Again, if I compute this, the coefficient is not changing. So if I do this in cross fashion, and I will be able to generate Y0 and Y1, I'm able to hold the coefficient constant for 2 clock cycle as well as the data constant for the next clock cycle. So now the inputs is changing at the multiplier at a lower pace compared to the previous one. For the previous one, the inputs are changing after every clock cycle, both the data input as well as the coefficient input. But by doing block processing, where you are processing two outputs at the same time and doing it in a particular order, by doing this, I'm able to maintain the coefficient constant for 2 clock cycle as well as the data constant for the next clock cycle. And this goes on and on. And this is a very effective technique to cut down the power consumption of an FIR filter. And I think we get some reasonable results for the full FIR course, 20-30%. 30% we get through block processing, compared to 20% through this coefficient segmentation compared to a normal conventional FIR filter for the carry save array multiplier and the non-booth Wallace tree multipliers. Now there's another concept. This is for the single multiplier architectures, and now we can think about a full-blown architecture, what's called the sharing multiplier concept. So this is the filter which is applicable to transport direct form, where the input xn is multiplied with all the coefficients. Again, the coefficients are fixed point. It's not adaptive filter, it's a fixed coefficient. So all these techniques are valid for the fixed coefficient filters and not for the adaptive filters. So what are the options here? How we can really go about it? Now, the big message is the same input x is multiplied to all the fixed coefficient. That's the mantra. And we can exploit this property for designing a low power architecture. Because now how we can do this? Now try to understand this concept. Now, the concept is like this. If I really want to multiply this 1011 into x, a 4-bit coefficient with the input x, I can do it like this. It will be, again, with the help of a shifter plus a multiplier. Because I think 3 we cannot do it, 3x we have to do it like a traditional multiplications. So 2 by 3 into, this goes to a shifter, and this goes to a normal multiplier. So if 011x and x are available, then the entire multiplication operation is reduced to a few add and shift. The whole idea is you replace multiplication through shift and add operation. And this is applicable to the transform direct form filter, since of the time limitations. I'll just give you an idea. So this is like pre-computer block in which you compute 1x. 3x you can always compute. It's like you shift left and add. 5x you shift left by 2 bits and add. 7x is like 8 minus 1, and 9x is 8 plus 1, and 11x is 8 plus 3, and then 13x is again like you can do 8 plus 4 plus 1, and like 15x is 16x minus 1. So these you can always generate. These are called the pre-computer block. Now you need this, all the odds one, like 1x, 3x, 5x, 7x, 9x, 11x, and 13x and 15x. And then once you have generated this, my job is like my coefficient is 8-bit, 110 and 010. Then I need two shifter blocks. This block to generate 0100 0100 into x, and then this shifter block will take care of the most significant 4 bits. The upper nibble will be taken care of by this block, and the lower nibble will be taken care of this block. And this pre-computer block, the big advantage is will be shared among all the multipliers h0 to hn minus 1. So let's say how I can compute this like 110 and into 0100x. So 0100 into x is generated by this block, whereas 110 into x will be generated by this block. So first of all, what happens how the 01000 will go straight away here, and this shifter will help you in generating 000, and this 0 means that 1x will come here, 1x will be selected here through this multiplexer, and then This shifter will generate two shifts here, so you'll get 0, 1, 0, 0 into X. And the same thing is repeated here. 1, 1, 0 will give me 0, 1, 1 will come over here, and 0, 1, 1 will take up here. It will be like 111X. 111X will be selected here, and this 111X will be available here, and then it will go there. Now in this adder, you have to shift this left by 4 bits and then carry out the addition. So in a nutshell, because of the paucity of time, I can't really go into the details. This pre-computer block will compute some basic multiplication for 4 bits only, and then we can extend with the help of these two blocks to 8 bits. Now the big advantage is this pre-computer block will be shared by all the multipliers. This is a shift and add block which I showed you. And this pre-computer block will be shared by all. So all the multipliers, a huge list, will be replaced by just one pre-computer block and only shifter and adder. So the whole idea is replace the multiplier by a complex multiplier which consumes a lot of power by a very simple shift and adder plus a pre-computer block, because this is an array of multipliers replaced by shift and adder plus one pre-computer block which is shared among all, because this generates all the basic multiplications and then the shifter and adder will generate the rest. That's the whole idea behind it. Let's move ahead. So this is a sharing multiplier. Now data representation, whether we can go for 2's complement representation. Remember that for 2's complement representation, the problem is if the input is switching quickly, then of course there's a lot of activity from +1 to -1. So if the inputs are changing a lot between from plus to minus, it's not a real nice representation from the power perspective. A sign magnitude is good if the input is changing a lot, but then it has other problems like subtraction is an issue. Now, so it's very important to explore different data representation before signing any system. Like if you have lots of multiplication, logarithmic system really helps. Only multiplication, because all the logarithmic numbers, they will change multiplications into, they can realize multiplication through addition. Now there is some interesting canonic sign digit representation where you have a +1, a -1, and a 0. And if you have that, we have noticed that it's possible to reduce to increase the number of zeros, especially for multiplication if you have canonic and sign digit numbers. And you know that in a multiplication, if you have more zeros in an operand, then the number of partial products will go down and hence the complexity goes down. So what people have shown that with a canonic sign digit representation, it's possible to reduce to increase the number of zeros in a multiplier compared to, let's say, a 2's complement representation, and that helps in power reduction. Word length has to be judiciously chosen. It should not be the same word length everywhere. If I have a pipeline structure, maybe I'll start with the lower word length, and as the data size picks up, then the word length can go on increasing. So I have to be very particular with the word length if you really want to minimize the power consumption. It has to be chosen after. It has to be properly selected for each and every block so that the error remains within limits along with the power consumption. Logic style, I think there's a dynamic logic is ruled out because at lower supply voltage, there's leakage issues. It has you need a pre-charge transistors. The acuity factor is also very high. So from the power perspective, as well as from the robustness perspective with the nanoscale, dynamic logic is not in. What is in is the static CMOS and the pass transfer logic, and these two has to be pursued from the power perspective. Asynchronous has big advantages because there's no clock power, but then asynchronous circuits are much bigger compared to the synchronous circuits, and there's a limited cache support available. Things might change in the future because they are difficult to design compared to the synchronous circuits, but then they have a lot of potential because there's no global timing. It's difficult to maintain global timing today. So the future is like it's globally asynchronous and locally synchronous. And moreover, the most important thing with the asynchronous circuit is they give you average case design. Synchronous circuit gives you always the worst case design. The critical path, the longest path will decide the frequency of operation in synchronous circuits. But in asynchronous, every module operates at its own speed. So it will give you the average case performance, which is much better than the synchronous circuits. Now, this is a very interesting design. I've just given you one slide and not the full details because of the time that I'm having. The cache-based architecture rather than feeding the information from the main memory, which is the case in the FFTs, because the butterfly needs all the data at the same time, starting from the first point to the last point. But then you can tweak the signal flow graph, come up with a new signal flow graph where the locality of data is maintained. So you need basically only the few caches will do the job. So the most of the time, the data is resident in the cache rather than in the main memory. So since the processor gets most of the data from the cache because of the locality of reference, this is the cache-based architecture is one of the most energy efficient architectures compared to a traditional. So this one paper was very attractive because they have proposed for the first time a cache implementation of an FFT architecture by just coming up with a new way of computing the FFT by tweaking the signal flow graph and ensuring that the locality of data reference is always maintained. Now, this is the last important slides I am having, and this is very interesting. I just want to devote 5 minutes on it. Approximate computing. This is something which is upcoming, especially for all the current applications, machine learning, video processing. We don't need exact processing. What is required is approximate processing. For all the machine learning, for all the big data problems, absolute accuracy is not essential because we can tolerate accuracy. So there are numerous applications coming up from the social media platforms, from the big data, from the neural network, from the AI, where absolute accuracy is not essential. We can sacrifice accuracy. So we can come up with a multiplier which can have errors in one or two, or maybe an adder which can give you one or two errors, especially in the sum, because in the carry we can't afford the error because the carry propagates from one stage to the other stage. So there's a point in designing approximate adders, approximate multipliers, which can give you much better delay performance, which will give you much better power performance, energy performance compared to an exact multiplier. So that is something which is very hard today. That's approximate computing. There's no need to really do the exact, because human perception, like videos, if few things are missing, you're not able to really figure out. There's not hardly any change, but then you get a maximum benefit, especially in the IoT setup where energy requirement is so important. Approximate computing is a big boom because that will help us in further reducing the energy to levels which is almost unthinkable for inaccurate computing. And this is one very interesting way of doing things. This slide shows a very interesting thing. Now, this slide shows, let's say if I take an adder as an example, a ripple adder to start with. Now, this block is an overscale hardware block. What is an overscale hardware block? Let's say if I have a ripple adder and I overscale means I've reduced the supply voltage of this block by a big margin. Supply voltage I have scaled very aggressively. When I scale the supply voltage very aggressively, errors, some of the bits which are especially the MSB, which have to propagate from all the LSB side to the MSB side, they will be an error. So for some of the combinations where the input carry has to move from the lowest side to the highest side, those bits will be in error in the overscaled hardware block, because this hardware block has the required precision that you need. And I want to do the approximate computing and not the exact computing. So, but let's say if it is 32 bits, and now I have a same replica of this, which is just 8-bit adder. But then I have carried out and this is basically a normal voltage, but this is like an overscale. I'm using this for at a very low VDD so that some of the MSBs of this will be an error. So now for all the normal data ranges where there's no need for the carry to propagate all the way to the MSB side, this hardware block will give you correct result. But then when the input has to carry all the way to the output, this hardware block will give me wrong result. So how to get the correct result? For getting the correct result, I have also a low precision replica of this. Now this low precision replica, which is let's say just of 8 bits, will give me quite decent results all the time. But then it may not be able to give me the required resolution Why? Because it's only 8-bit and I need much higher resolution, 32-bit. So what I am doing is, for most of the time, I'm getting correct result from the overscaled hardware block. For some, under some situations where the input carry has to propagate all the way to the output, for certain combinations, this overscaled hardware block is not giving me the required result. Under that circumstances, this decision logic will pick the result from here, because this will give you a more accurate result where this is in error. Whereas for all the normal circumstances, this will give you a correct result. So the decision logic will compare the two, and if the value is beyond, because if the MSB will be in error, then these two values will be radically different, and then the decision logic will decide from where the correct value can be picked up. So the decision logic will help in picking up the required value, whether the value will come from the overscaled hardware block or it will come from the low precision replica. And then there is, of course, so you'll be arguing that what is the real advantage? The advantage is the power of a 32-bit normal block will be very, very high. If it is replaced by overscale, where the VDD is scaled by a much larger margin, the delay has to be sacrificed. Some error will occur, but then the power of this block will be dramatically goes down. And of course, a low precision replica will consume much low power, and therefore the overall power of this design through this approximate computing is lower compared to if I just use a hardware block at the required precision level. So that is one way of reducing the power consumption through approximate computing. Other ways are just you can tolerate some errors in the lookup table as such, and then for some applications, and that is absolutely acceptable. So I'll just summarize future possibilities. Spintronics, a lot of MRAM, non-volatile, will give you really SRAM issue will be solved if we really move to the non-volatile power. Network on chip sensors is very, very promising, because that will give you an adaptive systems where you get you can tweak the supply voltage and threshold voltage very tightly in real time to get the best possible values for the power and at that point of time. And of course, we need transistors with higher mobility to get a higher ion-off ratio and low sub-threshold slope to operate at good speed. And thank you very much. If you have any questions, I'm ready for it. Hello.
Yeah, go ahead.
Yes. Now I'm asking if there is any questions, then I can take it, because I have some 5-7 minutes left.
Yeah.
So because this is what I intend to cover. Yeah.
Any question? I think that was there were two questions. Let's go back to this.
If you have any questions,
sir, you cannot see the chat box, no? Shall I read it for you? There were two questions earlier, I suppose.
No. I haven't been able to see the chat box. Yeah.
Okay.
Yes. Can I try it out?
I'll tell, sir. I'll tell. Will the multi-gate transistors address these problems of leakage current at low threshold voltages?
What? Can you repeat?
Will the multi-gate transistors address the problems of leakage current at low VT?
At low VDD, the multi-gate transistor. If you look at the tunnel FETs have a much lower. But I think for multi-gate also they are lower, but still the leakage problem is there. You can reduce it, but it has not been. If you really want to eliminate this leakage problem, I need, let's say, a transistor having 10 millivolts, 10 millivolts per decade of slope, so that even if I reduce the threshold voltage, let's say to 0.2 volts, is still for that 0.2 volt. If I draw that low subthreshold slope for VGS equal to 0, I should get drain current equal to 0. So multi-gate transistors like FinFET, they still have the leakage. The only thing is definitely better subthreshold slope than this, than the normal convention, but still You have leakage in those transistors as well. It's not slightly better subthreshold slope than a normal bulk CMOS. That's it. But still, it's there. Even with carbon nanotube FET, you have leakage problems. For tunnel FETs, they are able to reduce it, but then tunnel FET has so many other problems in the super threshold. You cannot have two transistors, one operating in sub threshold and the other operating in super threshold, because tunnel FET is designed for the sub threshold region. Yeah, but tunnel FET has promise if you really want to operate it in sub threshold or near threshold region. It's one of the most promising transistors that we have.
Anyone else? I think there is, yeah, but then that question, I don't know whether it was answered. It is quite old. It trade-off between low threshold voltage and a zero leakage current. But it was related to a particular slide Dr. Murthy has asked around 11 o'clock.
Okay, what's the question?
There will be a trade-off between a low threshold voltage and a zero leakage current.
Low threshold voltage, yeah. Zero leakage current you cannot get with the low threshold voltage. Zero leakage current means you have a high threshold voltage. You see, the problem is at high threshold voltage, like 1 volt, there was no leakage, because if you just draw the sub threshold slope, it will come out to be when VG is equal to 0, the drain current becomes 0. You get my point? So if you start moving the threshold voltage close to the ID axis, then this problem has come up. If there is a provision that we cannot, I don't have a choice to keep the threshold constant, because if I'm doing supply voltage scaling, I have to proportionally scale the threshold voltage. Otherwise, my drain current will dramatically go down, and my delay will dramatically go up, because the current will be so small. I don't know who has asked the question. Can that person be there so that they can?
Yes, Professor. This is Dr. Murthy asking the question.
Yeah.
Dr. Murthy asking the question. My question actually is, there is a trade-off. That means, is there any trade-off between threshold voltages and leakage current? My question is, as you go for low power devices, so when I have a device which can switch on at low voltages, when I prefer such devices, will it affect the leakage current? That's my question. That means, should we compromise between these two?
See, the problem is it all depends. If you have a device supply voltage, which is a device operating at lower supply voltage, then the dynamic power is related with the supply voltage. So you see, the total power is a combination of dynamic power plus static power. You get my point? So that we have to minimize the overall power consumption. You get my point? So we have to choose. You see, the problem is it's a very long topic. You have to choose judiciously the combination of supply voltage and threshold voltage. See, the problem is if you go on scaling the supply voltage and you go on scaling the threshold voltage, what happens? The dynamic power goes on reducing, but the static power starts rising, and therefore the total power is a combination of dynamic power and static power in a design. So the job is to minimize the overall power. That's a combination of dynamic plus static. So you have two knobs. The one knob is the supply voltage for controlling the dynamic power, which also controls the static power, because static power is VDD into I leakage, and you have threshold voltage, which directly controls the leakage power. So you have to set the value of supply voltage and threshold voltage such that the overall power goes down. Overall power is a combination of dynamic plus static in the design today. So the whole idea is to minimize the combination and not just one portion. The problem is if you can reduce one portion too much and the other portion rises, again, the overall power goes up. So it's just not like only dynamic, it's a combination of dynamic plus static power reduction. So the overall energy is the combination of these two, which has to be taken care of. Earlier on, it was only dynamic power, but today it's the combination of dynamic plus static, because static has gone up in a big way. And remember, dynamic power will go down in the future because supply voltage is getting scaled. So a bigger nuisance will be leakage power in the future, because unless we discover a transistor with a very low value of subthreshold slope and with all the other good attributes.
Yes, sir. Fine. Thank you.
I don't think there are any more questions. Anybody wants to ask any question? This question I could not get, madam. Yeah. Is there any specific graph related to static and dynamic power? What do you mean by that, ma'am?
I gave, yeah, I gave you the graph that
He was
like the
discussing
static power. Yeah, it all, yeah, of course, there are many graphs available between static power and, okay, can I share that slide?
Yes, sir. Yes, sir.
All right, I think there's a slide, I think maybe I'll try to get it back. If I can get it back, the slide. Look at this. This is like year after year, what is happening? The
Sir,
dynamic power is going down. And look,
sir, share,
yeah.
share once again. Share.
Or I think sharing. Okay, I'm not.
Yeah.
Maybe what's happening? I'll just check. Shall I share it? Yeah, I think this is a problem.
Yeah, it is there now.
Yeah. This shows now today the leakage power is around. You see the problem is the dynamic power is a variable thing. You cannot have one dynamic power. It all depends on the activity on the circuit. So dynamic power is not a static thing. It doesn't have a single value. It all depends on what is the activity that you are assuming in the circuit. If the activity is zero, the dynamic power is zero. And static power is something which is so dynamic power is not a fixed quantity. So it's very difficult to, you always plot the dynamic power as an activity. You have to assume some activity. And that's the reason why the runtime is important, because runtime is like the activity is variable. So if the processor is operating at high speed, then increase the VDD, reduce the VT. If the processor is operating at lower speed, then reduce the VDD. And maybe if it is standby, then power gate it or just remove the VDD from there at all.
Okay, sir. Okay.
All right.
Okay. Manish,
So I'll just summarize. The general trend is the dynamic power, since the supply voltage is scaling, the dynamic power is going down. So dynamic power trend is towards it's going down, and the static power, unfortunately, because of the nano scale, there are so many things coming up. The static power is becoming more dominant because this is not coming down, but since the dynamic power is going down, as a proportion of the overall power, the leakage power is playing a more active role today than the dynamic power. Because the dynamic power is going down. Why? Because the supply voltage trend is towards, let's say, is towards zero ultimately. It's not zero, but it's going down. And dynamic power is the strongest. Supply voltage is a quadratic function of the dynamic power is a quadratic function of the supply voltage. So that's the trend. So there are more papers on leakage today than on dynamic power. More bigger menace today.
I think over, sir. No questions.
Okay. All right.
I'll remove the sharing access rights from me.
All right.
Manisha, madam?
Yes, sir. Thank you, Dr. Hassan, sir, for an enlightening, interactive, and informative session. Sir has given us good insights of low power architectures for signal processing and communication. I hope participants have enjoyed the session. This was a good opportunity for us to listen you, sir. Thank you, sir.
Okay, thank you very much for inviting me to this talk and sharing my my knowledge with all of you. And hopefully, I think this sort of thing will continue in the future. And thank you for organizing such a nice event in such a diverse area over such a long time. Thank you very much.
Thank you, sir. Thanks a lot.
Thank you.
Yeah. So, participants will meet in the evening at 5 p.m. I'll be closing this meet.